recording? Okay. So let's get going on. Let's just go through part by part on linear transformations. How about I'll do my opening kind of thing about linear transformations, and then this is the first time I'm going to use this too. Here I have grid lines now. I realized I could do that. I'll do my little opening thing, what I thought of how to explain linear transformations. A few people have heard it before. So here it goes. So if we have R2, let's start in R2. Okay. So if R2, we have our standard basis vectors, right? So if I could draw it, well, I'll just draw it like that. Okay, so there's I hat, and j hat. And you'll see me drawing these many, many times, right? So if I were to do a transformation of this, right? So a transformation that goes from R2 to R2. An example of that, of what that could look like, is something like this, right? So it starts like this, and after the transformation, right? After the transformation, it could look something like this. So there's our origin. Origin is in the same place, and maybe I hat, or I call that one's j hat. J hat goes there, and I hat goes there, right? Or yeah, I hat goes there. Keep writing the wrong one. I hat goes there. So you can kind of think of this as the original space, right? Original / input space. And this is kind of the transformed / output space. And the really special thing about linear transformations, right? Linear transformations is that if I draw a vector here, if I draw a vector v, right? Where v, right? V here, and you can see here v is equal to 1 times I hat plus 1 times j hat, right? That's the linear combination of basis vectors that gets me v. That will still be true in the transformed space, right? So v would kind of look like something like this. It would be like about there or something. Well, okay, if it wanted to be that plus that, so I guess it would be there. That's how it would squish, right? And that will still be true after the transformation. V is still going to be equal to 1 times the transformed I hat plus 1 times the transformed j hat. So that's what we're doing when we're transforming things. Okay, just a very high level kind of thing, like without doing the math, right? That's what we're doing when we're saying we're transforming a vector. And how you'd write this transformation, right? The way you'd write this transformation is you'd say, well, where does I hat and where does j hat land? So in this case, I hat stays in the same spot, right? So I hat originally was 1, 0, right? 1, 0, 0, 1. That was this. So this is I hat, and that's j hat, right? And so you can see here, right? If it goes 1, 0, 0, 1 for those two. If I write where the transformed ones go, right? So this would be 1, 0 for I hat, and it looks like 1, 1. I didn't draw it perfectly, but it looks like 1, 1 for j hat. And so the matrix representation of this transformation is this right here. So if I wanted to take any vector from the original space and figure out where it goes after the transformation, I could just multiply it in the front here. That's how vector matrix multiplication is defined. Right? That's why it's defined the way it is. It's because it does this. Okay? And so, yeah, so this is where the I hat lands. This is where the j hat lands. Okay. So that's the... Okay, what else did I want to say in the start here? Linear combination. So the important thing is linear combinations are preserved, right? Linear combinations. So 1 times j hat is 1 times j hat plus 1 times I hat. Is the same at the end here. It's just a different I hat and j hat, right? It's transformed. It's the transformed versions. So, okay, let's move on to the textbook, right? So, let's see what happens here. So I'll just be scrolling through the textbook and just seeing what part by part is. So in general, the first chapter is kind of just what I said, right? We treat this process of putting in the vector v and getting out this transformed vector v as a function, right? You're putting it in and you're getting out an output vector. right? So it's saying this, it's just like a function from before, right? From calculus or whatever. So we write it like t, the transformation of the vector x, is equal to whatever the output vector is. But in this case, right here, I told you that that's the same thing as multiplying the matrix representation by v. Multiplying the matrix representation by v. So I can actually just take the matrix representation of that, right? Matrix rep of t, right? I can take that and I can multiply that by the vector x, right? The vector of the input. Okay, and so there's a bunch of special transformations that we'll get to and why it affects everything. But this is kind of like what, to me, and I think to like the whole point is like that's what brings together everything we do from the beginning of linear algebra, with like how systems of linear equations works and how determinants and like what a determinant is and like all that stuff. Geometrically, it'll be explained through this slowly, right? So the most important thing to get from 5.1 is pretty much this. T of x is the matrix representation of t times x. That's how we define matrix and vector multiplication. The important thing too is to tell if a transformation is linear. Sorry. If a transformation is linear, then t of ax plus by should equal a t of x plus b t of y. Right? A t of x plus b t of y. It's a plus there. And what this means is pretty much it preserves linear combinations. Right, good. So, okay, there's that. That's the transformation be defined by. I could do an example showing that something is linear. Yeah, I'll do that. I'll just see if I can find a good one. Yeah, okay. Just make sure we go through everything.
So just that first chapter is based around this like equation thing.
This it's based around just this idea of moving basis vectors to create another space. That's what it's based around. 5.1. Yeah, 5.1 is pretty much just based. I thought you meant all of chapter 5.
Yeah, just
5.1. Yeah, 5.1 is pretty much just this, and proving something is linear. Right. Let me make sure I start recording.
Quick question. So are we going to do like any numerical questions like they give us? Because honestly, I get the concept, but I don't really understand how to do this like algebraically.
Definitely. That's what I'm about to get to right now. So we're going to prove something is a transformation now.
All right.
Okay. So here's an example from Horowitz's lectures. That's probably what I'll just go with because that's what I have, right? So define this transformation, which takes vectors from R3 and puts them in R2, okay, as L of x, y, z, right, equals 3x plus z, 2y minus x plus z. Okay, a little nicer. And we need to show that this is linear. Good. And it is. So we can show that it is. So let's see if we can do it. I'll do it in 2 steps, but you could probably do it in 1 step. Maybe I'll try both. Let's see. We'll try to do both and we'll see. Okay. So what we need to prove that to show that's a linear transformation is that L of ax plus by should equal L of a times L of x plus b times L of y. We need to show that that's true. Okay. So let's start with that, right? Let's start with, we can just take the left side here, right? And apply this, right? So if I take a vector and I say x equals x1, x2, x3, right? And y equals y1, y2, y3. Okay? And I put that into here. So L of the left side, right, is going to be a times x will be ax1, ax2, ax3. And I'm adding that to by. So I'm adding each term b times y1 plus b times y2 plus b times y3. Okay. And the goal here is to prove that that's the same thing as this side right here. So, oh, it might be better to go backwards. Let's see how we're going to do this. So, a L of... Oh, yeah, okay. So let's apply the transformation to this. Yeah, let's apply the transformation to this. So if I apply, so if you see that's what the transformation is defined as, 3x plus z, 2y minus x plus z. Okay, so the important thing here is that the x's just really mean the first position, the z's mean the last position, and the y's mean the second position, right? That's what really matters. So L of that is equal to, okay, so the 3 times the first position, 3 times ax1 plus by2 plus the last position, which is ax3 plus by3. And the second thing is 2y, so 2 times the second position, ax2 plus by2 minus x. So minus the first position, which is ax1 plus by1 plus the last position, ax3 plus by3.
Wait, wouldn't it be 3ax1 plus by1?
Yeah. 3 times, yeah, I don't know why I wrote 2 there. Yeah. And let me just make sure I got the rest right. 3x, so the first position, 3 times the first position, yeah. Plus the third position, yep. 2 times the second position, minus the first position, plus the last position. Yeah, okay, so we're good now. Thank you. So what I'm trying to do, right, is I'm trying to prove that it's the same thing as this plus this, right? So I want to separate a times L of x and b times L of y, right? So if I multiply this out, right, if I multiply this out here, so if I'll just go to the next line, it's going to be 3ax1 plus 3by1, yeah, plus ax3 plus by3, okay, 2ax2 plus 2by2 minus ax1 plus by1 plus ax3 plus by3. Okay. And so now 3x1.
Would it be minus by1? Second line?
Second line minus by1. Yeah, yeah, that's right. Minus by1. Yeah, that's good. So I want to break this up into something that looks like this, right? So a times L of x1, right? So if I move all the x's together and all the y's together, right? So it's its own thing. So it's going to be 3ax1 plus ax3, right? Plus 3by1 plus by3. Okay, again, so I put all I did there is I switched the positions. So the x's are together and the y's are together. 2ax2 minus ax1 plus ax3, okay, plus 2by2 minus by1 plus by3. So again, all I'm doing is I just switch the positions of the things there. Well, now what we can do is we can separate this into two vectors, right? This is the same thing. I'm not changing anything by doing this. Look, I'm going to take 3ax1 plus ax3, 2ax2 minus ax1 plus ax3. Okay. Just the x vector. And I'm going to move that to the side so I have a little bit more space. I might need even more space, so I'll just erase those equal signs. Come on. Right? And I'll just be adding this to another vector, right? I'll just be adding this to the y vector, which is 3by1 plus by3, 2by2 minus by1 plus by3. Okay. Well, now out of this first one, I can factor out an a, and out of the second one, I can factor out a b, right? So it's really a times 3ax1. Oh, no, I factored out an a. So 3x1 plus x3, 2x2 minus x1 plus x3 plus b times 3y1 plus y3, 2y2 minus y1 plus y3. And the thing to notice, the reason I did that is because look, what would just L of x be, right? Just x. So x was x1, x2, x3. L was x1, x2, x3. So if we go back to our definition of what L does, right? L does this, right? So just if I were to just apply this just to the vector x1, x2, x3 here, I'll just copy this down. I'll bring this down over here so you can see a little bit better. Right, and then I'll hide it after again. Come on. Okay, can't copy. Oh, I can paste it up here. That's not where I want to paste it, but I guess that's what I'll do. Okay, so if I were to just apply this thing to this transformation to just x1, x2, x3, it would look like this. It would look like 3x1 plus x3, right? Because it's taking it wants the first position and the third position, right? 2 times the second position, x2, minus the first position, plus the third position, x3. But exactly what we have here. So in other words, if I just move this over, right? If I just move this to the side, in other words, what we have is this is a times L of x1, x2, x3. Similarly, for the same reason, this is b of L of y1, y2, y3. And just one more step, just because up here I defined the x vector as that and the y vector as that, right? Then I can just write this as a times L of x plus b times L of y, right? And since these are all equal, I've just been forgetting to write the equal signs, right? What I've proven is that this, in other words, this is equal to this. A of L of x, A times L of x, plus B times L of y. That's what I got down here. A times L of x, plus B times L of y. So therefore, it is a linear transformation. So that's the question done. Any questions?
Quick question.
Mm-hmm.
Sorry. So basically, this allows you to combine both preserved under addition and multiplication the way you wrote it.
Yeah,
So you
this
don't
I
need
did.
to
I
do
did. I
anything.
did both tests in one here. I did both tests in one go.
Oh, actually works really nicely.
Mm-hmm.
Because CPW split it up.
You
Thank
can
you.
split it up, and
Wait.
if someone wants me to split it up, I can do that too.
No. I'd say like I like this better because it's just one thing.
Yeah.
Can you go down to the part where you actually like got it to match the definition?
Mm-hmm.
It was this one, right?
It's right here. This pretty much this line is the last line. I did some algebraic, moving things around,
Yeah.
and then the next line. Well, this is L of x1 or L of x, and this is what L of y would be. So I can just
Yeah,
write
and it matches what it said, right? The x1 plus x3. in the
here
definition.
in the here's the definition. I wrote it again.
3x1.
Right,
Oh.
and it's 3. There's a 3 there.
Oh, okay. I see.
Right, there's a 3 there. So it matches the definition. So I can just replace it with L of x1,
Oh,
x2, x3, y1, y2, y3.
Wait, is that basically saying L of some vector is gonna give you, scroll down a bit?
Down?
Yeah. Yeah, just gonna give you this linear transformation, and each of them is just corresponding to the component. So it's in R3, so it's gonna be X, Y, and Z, R, X1, X2, X3.
Yeah, so it's just saying L of this three-dimensional vector, so it has to take in a
Yeah,
three-dimensional vector, right? Yeah, and so if the X, the X, all that really means in the definition is the first position, the thing in the first position, right? And
yeah,
the Y is the second
Yeah.
position, and Z is the third.
yeah.
Okay. So, okay, there's that one, showing something is a linear combination, a linear transformation, by showing that it preserves linear. Can't say the right word. Linear combinations.
Could you scroll up a little bit?
Up?
Just like, oh wait, down, a little down. So wait, why is it Z there for like the B? Shouldn't it be like Z for like the top, right? Like,
This should be a 3.
okay.
Is that what the confusion was? Yeah, that should be a 3.
No.
Right, so that would be a Z. That would be like the bottom value, right? The third value, and so that corresponds to the definition too.
Oh, okay, alright.
Right.
Okay, I got a little confused.
Yo, wait there. Was this an R3 to R2, right?
Mm-hmm.
Okay, I thought you had R2 up top.
Oh yeah,
Okay.
did I write that? No, R3 to R2. Yeah, R3 to R2.
Okay, my bad. I'm just blind.
Don't worry. Okay, so the only other thing from 5.1. So I'm just gonna go through the lecture notes. That's pretty much what I'm gonna do, honestly, because I think I like that better than there's like good examples mixed in. So the only other thing from 5.1 that I have is the zero transformation, which is just L of x equals the zero vector for all x, right? Well, for all x ERN. So all that's saying is that there is a transformation called the zero transformation that doesn't matter what input you put in, it will output a 0. The matrix representation of that would be 0, 0, 0, 0. In R2, sorry, in R2. And I think you can guess what it would look like in any other R, just all zeros. Because basically what you're saying is that you're starting with your standard basis, and then after the transformation, all the standard basis vectors are just at 0. Right? So everything collapses to 0.
Wait, is that saying that the transformation is like a matrix that's like a zero matrix?
That's what it is here, right? Exactly, yeah. It's just a zero matrix, right?
Okay.
That's exactly right, yeah. It's all zeros. And then there's only one more that I have here. And that's just that there's the identity transformation, which is written like this, IDN, which goes from Rn to Rn. And all that is that L of x equals x for all x, E, R, N. So it just does nothing. The identity transformation in R2 looks like this, which should look familiar. It's the identity matrix, right? It's the identity matrix for in R2. Right. Okay, and that's pretty much it from 5.1. So any questions, any homework questions people want me to do or anything like that, I will do them. Very thirsty for some reason. Okay. So I'll take that as a no.
I have a question. So
Yeah.
you know how you put the equation to ALX plus BLY? So by putting
You hear this? Yeah.
yeah, so by putting the A and B, that means you're confirming it under the multiplication, and then by adding X and Y, that means you're confirming it under addition.
Mm-hmm. Separately.
So if you want to split it up, you would just do LX plus LY, and then in the next one to do multiplication, you would do ALX.
Yeah, let me write it here so it will make more sense, right? Yeah, so if I want to prove I have some linear transformation that goes from R2, or it was from R3 to R2, then I want to, well, it doesn't matter really, but I want to prove that separately, L of x plus y equals L of x plus L of y. That's my first proof. And my second proof is that L of ax is equal to a L of x.
Okay. Okay.
But what I did is I just combined them both into one.
Yeah. That's
Wait.
probably more efficient.
Is the point of this to like show them the linear combinations, or that it works, or are we actually doing the transformations in 5.1?
Well, we're not actually doing, because it doesn't give us a vector, right? It doesn't give us a vector to prove it. And even if it gave us a vector, just the fact that one vector preserves linear combinations doesn't mean that every vector would. So you're just trying to use the definition of the linear transformation, or of the transformation, not just linear, to prove that it's linear. You're proving that it's linear by doing this. Does that make sense? Or did that make sense?
Yeah, no.
So, here, let me look if there's anything else. Let's see in the textbook for 5.1. See if there's anything else here. Prime 2R3 transformation. Okay, I think that's it from 5.1. So yeah, so just the only thing is just this. It's just pretty much this here, right? So we have a transformation. We don't know if it's linear. To prove that it's linear, these two things have to be true. And to show that, well, you just make up a random vector, and I called x equal to x1, x2, x3, right? And I called y equal to y1, y2, y3. So these are any vectors, right? Any vector in R3, right? Because that's in R3 because that's where the input is. And then I did the transformation because it was defined in some way, right? It was defined at the beginning of the question. And I just did the transformation that this tells, and I showed that it's the same as this. And then separately, do the transformation of this, right? Multiply x by a, do the transformation, show that it's the same thing as this. But what I specifically did was combine that into one. Right? So yeah. So I guess let's move on to 5.2. That's good with everybody. If there's anything else. 5.2 is talking about how you can write some matrix A is equal to the matrix. Yeah. Any linear transformation as a matrix transformation, right? And so what that means is that any linear transformation T of x can be written as A times x, where A is equal to the matrix representation of T. And that's what this means, right? So the matrix representation of the transformation T. In other words, it's the matrix that when you multiply a vector by that matrix, it does the transformation. So the important thing to get from this, and relating back to what I said before about, you start with your standard basis, and after the transformation, the standard basis goes somewhere else. It's pretty much what I was saying was what 5.2 is talking about, is that to figure out the matrix representation of a linear transformation, you just apply the transformation to the basis vectors. Right? And see where they go. And the columns, where they go, will be the columns of the new vector, of the new matrix. And so yeah. So let's do an example of that. Okay, so the actual definition is that the matrix representation of L is equal to the matrix whose columns are, first column is L of E1, and that's the column. L of E2, that's the column.
Wait, that line doesn't mean anything, right?
It doesn't mean anything except that that's the whole column. That just means
okay.
The whole column is this vector, right? L of E2. And L of E3 right? If the transformation goes from Rn to Rm. Oh, then shouldn't it be M? E's are all standard. No, it looks like it should be N. Times X, yeah. So we're going from standard basis of, oh, that actually makes sense. Never mind. Yeah. So the L is defined from Rn to Rm. Right. So this N is how many standard bases, base I guess, you have to apply. So let's do an example of that. Right. So the example is this one. So L goes from R2 to R3. Yep. So and it's defined like this: L of xy is equal to x plus 2y, y minus x, x. And let's say we know it's linear. Okay, let's say we know it's linear. So we want to find the matrix representation of L now. Okay, we want to find the matrix because we know it's linear, so we know that there is a matrix representation of it. So to find it, well, we just have to apply L to each of our basis vectors. So L of E1 we need to find, and L of E2 we need to find. So the 2 from R2. So applying that to here, so remember E1 is 1, 0 in R2. And so that's E1, E1, and E2 is 0, 1. So applying this, right, it's going to be the first entry plus 2 times the second entry. So the first entry plus 2 times the second entry. The second entry minus the first entry. The second entry minus the first entry. And then just the first entry. Right? Boom. So that's what L of E1 is going to be, right? So we can simplify this a little bit. It's going to be 1, negative 1, 1. Right? That's what L of E1 is. And L of E2 is going to be a similar thing, right? So E2 is 0, 1. So the first entry plus 2 times the second entry. The second entry minus the first entry. The first entry. Right? So that's 2, 1, 0. And so our matrix representation of L is going to be 1, negative 1, 1. Oops. 1, negative 1, 1. 2, 1, 0. Good. So that's the matrix representation of L. And that's the answer to the question. So that's everything. And so if I wanted to like transform a vector in R2, let's say I wanted to transform, like, I want to know where does the vector, I don't know, well, no, not that, but I'll go to, I don't know, 2, 1. Where does that go? So what's L of that? Well, then I would just do 1, 2, negative 1, 1, 1, 0, right, times 2, 1. Right, which is just 2 times 1, negative 1, 1, plus 1 times 2, 1, 0. So that's 2 plus 2 is 4. Negative 2 plus 1 is negative 1. 2 plus 0 is 2. So that's where the vector would go. If I inputted this vector, I would get this vector as the output. Right? Okay, guys, I'll be back in just 1 second. I have to unlock the door. Sorry. 2 seconds.
Anyone else think Adam's like Khan Academy?
He teaches better than CPW.
He
CPW right now.
CPU
I
just use
stopped
the
going to his lectures like 3 months ago.
Hey, don't disrespect the goal like that.
Didn't
CPU
university start 3 months ago? What the
Can you scroll up for a second so I can see the? Because like I didn't really get the E thing. Are you saying that each column is like E1, E2, E3, and this is what each of them represent?
Here, this part right up here.
Yeah.
Yeah. So all that's saying is that the matrix representation of L, the transformation L, is another matrix, right? That's what the square brackets here, right? Where this is a column. This whole thing is one column, right? This is another column. This is another column. Each of the columns is just L of the standard basis in order. 1, 2, and then up to n, whatever n is.
Oh, and we just go by like the.
And the standard basis, right? The standard basis is written like this, right? It's just pretty much like if I draw R2 and I draw the basis vectors like this, that's the standard basis. I hat, J hat. It's just 1 in each direction, 1, 1, right? And so you'd write this vector as 1, 0, right? And you'd write this vector as 0, 1.
Okay, so you had to like En, so that would just be like, let's say it was that would this. You started from R2, so that's why we just did the first two, right?
Exactly. N is the input R, right? That's Rn of the input. Right? So for this example, it started in R2, so I only had to apply it to L of E2 and L of E1 and L of E2.
Yeah.
Okay, that makes sense?
Yeah.
Okay.
So you always use the standard basis, right?
Yeah.
Okay.
And you can use a different basis. Not quite. I guess you wouldn't. No, I guess you wouldn't, unless you know what you're doing, which is I think maybe a later chapter. Which is kind of like what the rest of the stuff is also based on. It's just that they don't really talk about it as if you're like moving basis vectors. But when we get into the whole P inverse AP thing, which is right, chapter 7, right? So that it's good to always try to think about the matrix as moving the standard basis vectors, and it kind of helps.
The E's are basically just each like for the standard basis, it's basically the identity matrix of each like column, right?
Yeah, I guess you could call it. I don't know if it's called that, but yeah, you can treat it like that. It's En.
Or like each R, like R2 would just be 1, 0, but R3 would be 1, 0, 0.
Right. So En is a vector with zeros in every position except a 1 in the nth position.
Yeah.
Right. Does that make sense? So this is the first position, second position, third position, right?
Yeah.
So E1 is just, and then you also have to kind of know what like Rn you're in, right? So E1 could just be 1, but since we're in R2, it makes more sense to call it that.
Yeah, makes sense.
And if you were in R3, it would be that.
Yeah. Thanks.
It's just the identity matrix, right? For
R2.
Definitely.
Well, it's not really the identity matrix, because identity matrix for R2 is 1, 0, 0, 1. But this is, the reason it's the identity matrix is because this is just E1, and that is just E2. Right?
So if it was R2, E1 and E2 would be that, but if it was R3, then it would be the
it'd be 1, 0, 0, 0, 1, 0, 0, 0, 1. And so now E1 is that, E2 is that, and E3 is that.
Okay.
This is in R3. And this is in R2.
All right, yeah, that's clear.
Okay, good. So, that's our example.
Wait, that was an example, like a numerical question.
Yeah, that was because for up here we found like We found the matrix representation of L. That was what we were looking for, right?
Oh yeah, and then you just did for 2, 1, right?
I just made that up. I just said like, okay, well, if we wanted to take this vector and move it, like where would it land after the transformation? Well, it would land at 4, -1, 2.
Yeah, cool.
So what does the 4, -1, 2 represent? Is it
Well,
like the vector at that point, or?
Yeah, so pretty much in R2, right, the input space is R2. So where all the stuff that you input is going to be a two-dimensional thing. It was at 2, 1. So let's just say 2, 1 is like, well, it'd be 2, 1. So like something like that, right? Let's say that was the input vector. And then the output vector after the transformation is going to be, I can't draw it because it's in 3 dimensions, but it would be at that position, right? X, Y, Z.
Beauty. Okay.
Right? That's where the end of that's what the tip of the vector would be at.
Oh, okay.
After the transformation.
So it just represents the vector in like R3, pretty much.
Where it represents the vector after the transformation. After the transformation.
After the transfer. Okay.
Yeah. Right. Yeah. Because the same vector could be moved to somewhere else in R3 with a different transformation. If you just define the transformation differently. Right. So it would move somewhere else in R3.
All right. Makes sense.
No problem. So, there are some just like weird questions that are unnecessarily weird.
So you could think of 2, 1 as like 2, 1, 0, where the Z is 0. And like it's not in R3, but like you could think of it like that to understand the transformation, right?
Yeah, but that kind of makes it seem like you're going from R3 to R3, right? That kind of makes it seem like it's already in R3 and then you're moving it to R3. But that's not the case. It was in R2. It was in a completely flat plane like this. And then it got stretched into 3D space.
So if you got a vector 2, 1, 0, it's different from just 2, 1?
Well, it's not actually different. It's not actually different, no. And you would just run into a problem with this. Well, you wouldn't. I guess you wouldn't really run into a problem, but it's not actually like it's not a different vector, right? But if you did that, then to try to multiply it, you'd have to do 2 times this vector, right? 1 times this vector, and then you'd be stuck because you can't do, even though it's just 0, you can't do 0 times. There's no other vector, right? There's no other thing, here, right? So, like, although this is the same vector. 2, 1, 0 is the same vector as 2, 1. It wouldn't work in this question because the linear transformation is defined from R2 to R3.
Right. Okay, that makes sense. Right. Yeah, I didn't think of it though.
Right. So yeah. Okay. Looking at the notes here for a second. So another thing is a procedure, which is that if, okay, so I'll probably just write it out and we'll see. So it's a procedure to find the basis, right? To find the matrix representation of T. So suppose you have a transformation T from Rn to Rm. Okay, and you know all of the transformed versions of the basis vectors. So if we have a basis for Rn, call that a set, call that this set, where right, so it's A1, A2 dot 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 An, right? If I have a set that's all the basis vectors for Rn, right? And I know what each of those transformed basis vectors are, right? I know what each of those transformed basis vectors are. TA, BI for each. Oh, yeah, okay. Okay. I know what all these basis vectors are, so it's going to be B1, right? T of A2 is equal to, I shouldn't use arrow, equal to B2. And T of An is equal to Bn, right? The important thing here is that this doesn't have to be the standard basis, right? This can be not the standard basis, right? This can be just any basis for Rn, right? Then we can calculate the matrix representation of T by doing this. We take the output space, right, the output vectors, all of them, put them in order in a matrix, right? So we make a matrix like this. B1, right? So again, these lines just mean it fills the column. B2, right? This is a vector that fills the column. Dot, dot, dot. Bn, right? And multiplying that by the inverse of the input vectors, the input space, arranged in the same way. So A1, A2, dot, 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 AN. But the inverse of it. Okay? And so if you want to think about it, like this, like with visually with the transformations, what we're doing is we're saying this basis for Rn is already transformed, right? It's not the standard basis. So you started with the standard basis. This, and let's say after the transformation, it looks like this. This is still a basis for Rn, right? This is still a basis for Rn. It's a different basis for Rn, right? It's not the standard basis, so this is standard. And this would be an example of this setup here, right? Let's call that big A. So that would be an example of A, right? And so what you want to do first is undo this transformation. That's what A inverse does, right? So applying A inverse to this, right, would get us back our things, right? And then we want to know where should these vectors land after the transformation. Well, that's the outputs. Right? That's where the vector should land. And so then we apply that transformation to this, right? We apply B to that, which is this B section here. Right? So that's A inverse B. So that's what we're doing. We're undoing the transformation that got the vectors into that basis, and then just applying where they should land, the output of the transformations. Right? And then calculating this, doing this multiplication would get you the matrix representation of just this pure transformation, right? Just this transformation. Okay. So one way to calculate this is to put all the A vectors, right? A1. So sorry, this is one way to calculate this. Another way to calculate this, which is simpler. It's the same idea. It's just that you take all the A vectors, put them A1, A2, A dot 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 AN, right? And you augment it with the B vectors. B2 dot 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 BN. And if you put this in RREF, right? What you should get is, if it successfully got into RREF, what you should get is that here you have IN on the left side, right? That's what RREF is, right? 0, 1, 1, 0, 0 is an example in R3, right? You should get the identity matrix size n. And you want to augment, and you want to see that augmented with some other matrix, which is going to be the matrix representation of T. Which is what we were looking for to begin with, right? So we'll definitely do an example of this. We're not just doing it for no reason, but yeah, definitely do an example of this. Let's see, yeah. So yeah, so that's that. It's similar to how you find the inverse of a matrix.
So just a quick question. If they're asking us to find transformation matrix, we have to do the, like if they give us transformed vectors, we have to take the inverse of the original, like what it's asking us to transform, and then take the inverse of that multiplied by the transformed ones. Right?
Multiplied by the outputs, yeah. The inverse of the inputs to get it back to standard, and then multiply that by the transformed ones to know where it has to go.
Okay, because I feel like that's mostly going to be what the questions are going to be on. So.
Yeah, I think this is going to be I think this is going to be on the test. This kind of idea of doing this procedure. And for some reason, which I don't quite know, but I feel like I'll learn soon, is that these are equivalent, right? So I said these were two ways of doing it, but these are equivalent. Multiplying B by A inverse is somehow, again, I don't really fully understand, but it's equivalent to doing this process of putting A here, B here, row reducing, and getting T.
So just to clarify, you find the inverse of A, then you multiply it by like the V, B matrix, and then you get whatever.
Yeah, that multiplied together will be the matrix representation of T.
Oh, okay.
That
And then is there anything you do after that, or is that just your answer?
If the question just asked for the matrix representation of T, then that's all you need, right? That's all you would.
Okay.
That's all you have to get, right? Any other questions about this stuff? We'll do an example now, but.
Yeah, do an example because I'm not getting it with the letters, right?
So let's do an example. So if I have, I know that T of 1, -1, 0 equals 2, 1, 1. I know T of, this is a separate points. So T of 0, 1, 1 is equal to 0, 1, 1. Wait, 0, 1, 1? Oh, okay. Right. And I know that, is that really supposed to be T? Yep, I guess so. T of 1, 0, -1 is equal to 2, 0, -4. So I can't use the thing we did before, where it's like apply T to all the standard basis vectors and get that matrix like that, because I don't know exactly what T does, right? I don't know. Because I don't know like the exact formula as in like T, X, Y, Z equals something, right? Something happening to X, Y, and Z. Right? I don't know what that is. And I can't guess. But I can still figure out the matrix representation of T just from this. So like I said up here, the way that I'm going to do it is I'll do it this way with the row reduction because I don't want to do multiplication. So we take all the input vectors. So that's this, this, and this. Put them on the left side of a matrix. Okay. 1, -1, 0, 0, 1, 1, 1, 0, -1. And augment that with the output vectors. Right? That's what I said over here with the B's, right? All the output vectors. Okay. And so the output vectors are 2, 1, 1, 0, 1, 1, 2, 0, -4. Yeah. Okay, and so now we just put this in RREF. And ideally on this side, we should get the identity matrix of size 3. Right, because we're in R3. And on this side, if I can do that, this side will be the matrix representation of T. So let's do that. Let's get this in RAF. So I will keep the first row, and I'll do row 2 plus row 1. So it'll be 1, 0, 1, 2, 0, 2, 0. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 2 is 3. 1 plus 0 is 1. 0 plus 2 is 2. Okay, and the bottom stay the same. 0, 1, -1, 1, 1, -4. Augmented with that. And then I will do row 3 minus row 2. So 1, 0, 1, 2, 0, 2, 0, 1, 1, 3, 1, 2, 0. 1 minus 1 is 0. -1 minus 1 is -2. 1 minus 3 is -2. 1 minus 3 is -2. 1 minus 1 is 0. And -4 minus 2 is -6. Okay. I'll do row. Well, okay. How about I write it like this? If everyone's okay with this, I'll do -1/2 row 3. Well, just to keep it not confusing, I'll write it all again. So -1/2 R3. 1, 0, 1, 2, 0, 2, 0, 1, 1, 3, 1, 2, 0, 0, 1, 1, 0, 3. Okay, we're almost there. Row 2 minus row 3, row 1 minus row 3. So 1, 0, 0. 2 minus 1 is 1. 0 minus 0 is 0. 2 minus 3 is negative 1. Okay, 0, 1. 1 minus 1 is 0. Okay. 3 minus 1 is 2. 0 minus 1 is 1. 2 minus 3 is negative 1. 0, 0, 1, 1, 0, 3. Okay, so we are now in RREF. We successfully got this side to look like I3, right? And so what that means is that this is equal to the matrix representation of T. So the matrix representation of T is 1, 2, 1, 0, 1, 0, negative 1, negative 1, 3. And yes, I did it right. So that's the matrix representation of T. And now with this, we can apply this transformation to any vector in R3, right? Because this is a transformation from R3 to R3, right? So I can apply it. So not just to begin with, we only knew what the transformation did to these three vectors. But now I can apply it to any vector, because remember, T of any vector x in the input space is equal to the matrix representation of T times that vector. And now that we know the matrix representation of T, we can do it to any vector in R3. Okay. Yep, that seems like it's it for 5.2. I'll have this. Any questions about this stuff I just did right here? And I can do another example if people want me to do another example.
Yeah, just to be clear, you did the scroll up a bit to the actual, yeah. So you just put this on the left, and then the actual output on the right, and then we just did reduce to get the actual T.
Yeah.
All right, bud.
Yeah, that's that, right? And so then I RREF. This side is identity matrix. This side is T.
And then we can just use that to use for any other three vector. R could be R2 as well. We just get something different, right?
You couldn't use this transformation for R2 because this transformation is defined from R3 to R3. Let's see what happens if I try to do it with R2. Let's see what happens if I try. So if I'm saying I'm going to try to find T of 6, 5, okay? That means I'm going to take this matrix, 1, 2, 1, 0, 1, 0, negative 1, negative 1, 3, and multiply that by 6, 5. So standard matrix vector multiplication is going to be 6 times the first column plus 5 times the second column plus, and I'm stuck. I have nothing to add. I have nothing to add to the third column.
You can't just say 0, yeah.
You can't just say 0 because it's just you'd be putting a number there, right? But we don't know that it's 0.
Yeah, that makes sense. I'm just medicine. How Professor Horace is probably gonna put like A, B, and C or some shit like that. That's like, oh god.
Yeah. Well, so then that's different, right? So you got to use your algebra skills for that, yeah. Which is difficult.
No.
Which is difficult.
So this is to define what the transformation is.
Mm-hmm. This is to find the matrix representation of the transformation.
Okay.
Yeah. Right. So if I had a vector in R3, right? If I put a 2 here, then I could do it, and it would give me some vector, right? It would give me some vector. But since this one was in R2, it wouldn't work. But this one does work, so whatever. This one would be 6 plus 0 minus 2, so 4. 12 plus 5 minus 2. 12 plus 5 is 17. Minus 2 is 15. 6 plus 0 plus 6 is 12. So there you go.
All right.
I always spill water when I'm on the live stream for some reason. Luckily, I just missed the papers. Perfectly missed the papers. Okay,
The way for 2 seconds. Where did 2 come from?
I just put it just for an example in R3. I just put it.
okay.
I just put it. I chose that. Right. I picked that. Oh no, a little bit did get on the paper. Okay. Well, what can you do? Just a little dot. Okay. So that's it for 5.2. Okay. So 5.2. Any questions from 5.2? Or about what
Can we use the same method if we're going from R2 to R3?
Yeah, it doesn't really matter. Actually, hold on. Yeah, so then if you can make this matrix, yeah, let's say. So if you're going from R2 to R3, then you'd have a two-dimensional vectors for the yellow ones. Then you wouldn't really be able to make this reduced row echelon form thing. Right? You wouldn't be able to make this augmented matrix. So no, I don't think so. I think you have to be going from R3 to R3 or Rn to Rn.
Yeah.
Okay.
Although it does say... Oh, no. In that case, I think... Huh. It does say it... it has this. So, sorry, and an important thing that I didn't actually mention is that the yellow vectors have to be linearly independent. They have to be linearly independent. They have to form a
How do you know
basis
that?
for R3. I didn't know that. I know it just because the question says that they are linearly independent. But
Okay.
they have to be because they have to form a basis for the input space. They have to form a basis for the input space. So what would you do if you were going from... Because it does say the transformation goes from Rn to Rm. So it does say that things can be different. From 1 to n...
Would you have to use the other method then? We do the output times the inverse of the...
I was thinking that, but that doesn't always work either, right? That doesn't always... Because you wouldn't have square... No, you would have square matrices.
I was thinking that inverse thing, it would work if you had only two transformations, because then you would be going from R2 to R3, but you would only have two transformations, so you'd have the same columns and rows to do multiplication by.
Yeah, I like an example like that, though. I like an example. Is there an example maybe in the book here? Let's see.
Also, the examples are R3 to R3, R2 to R3.
Yeah, it looks like it, Ryan.
Yo, earlier you said something has to be without free variables, right? Or something like you said, like independent. That's what you said, right?
Yeah, they have to be the yellow vectors have to be independent. The input vectors.
Yeah. Okay.
Yeah, because they have to form a basis for the input. The inputs are 3.
No variables.
Right. So I don't really have any. I don't know where my practice problems went here. So this is 5.2, which is 2.6.7. 2.6.7.
How about just make your own example, see how it goes?
Well, I can try, but the chances of me just screwing up making the example would. Well, yeah, we can do it. If I can't find anything.
Do a Horowitz, Adam. Do a Horowitz. He does
That's
this
what
all the
Horowitz
time.
does.
Yeah.
He literally makes his own shit up.
That's true.
Yeah, just
And
do a
changes it 5
Horowitz.
times during the actual problem solving, session. So.
Yeah,
That's
just
fine.
do it.
Okay, I'll try. If I can't find, I'm just looking at the color stuff, and if I can't find it here, the Nicholson stuff. So, T is linear. Find. Nope. 4. Oh, here's one. R2 to R3. Yep, here's one that is what we're talking about. Yep, and I did it. 14b, yeah, I did it. So let's see what it looks like. So this is 7.1.4 or no, B from Nicholson. Okay. And so what this gives us is it says, well, B is saying that there's a transformation. I don't write B again. Transformation that goes from R2 to R. Oh, yeah, no. There's a few ways to do this actually. R3, and it's defined like this. So T of 2, -1 is equal to 1, -1, 1. Okay, and oh, I see how it will work always. Okay, yeah. because that would
I
be
think T itself has to be in the same like R dimension as the one you're trying to find.
T itself.
Yeah.
T isn't really in a dimension. Oh, you mean the matrix representation of T? You mean like the? Yeah. Well, yeah. It gets to the size. The exact size of the matrix representation of T is important, and we'll get to that in just a second. So this is. Oh, I didn't copy it right. 2, -1. 1, -1, 1. That's right. This is 1, 1. And this is 0, 1, 0. Okay. So the question is find the matrix representation of T and then calculate T of V, where V is -1, 2. Okay, so find matrix representation and then calculate T of V, where V is that. So first with the matrix representation, yeah. I think we're going to have to do the multiplication method, right? So we take the input space, 2, -1, 1, 1, right? One thing to note is that these are going to be linearly independent, right? Pretty clear to see that that's true for these two, right? It's not too hard when they're in R2 and there's only two vectors, right? They're linearly independent, right? And so we want to multiply that. Oh no, we're doing the multiplication method. Sorry, we're doing the multiplication thing. So we take the output, 1, -1, 1, 0, 1, 0, right? And we multiply that by the inverse of the input space. 2, -1, nope. 2, -1, 1, 1. The inverse of that. And so you notice that this is going to work because this is 3 by 2 and this is 2 by 3. And when you're multiplying, these have to match up, right? And this will always work because this has to form 2 by 2. Yes, I do mean 2. I do mean 2 by 2. This will always work because they form a basis for R2, right? These form a basis for R2. Yeah, that's what I mean to say. And this is always going to be two vectors if this is in R2, right? You're always going to have just because it's defined by two things, right? If, for example, you had a third one, like T of 2, 6 equals whatever, 5, 3, 2, well, sure, you could put this in here and then add another one. But the problem is that this is not linearly independent anymore. This is not linearly independent, right? It won't be. So, because this doesn't add anything to the span. This doesn't add anything to the span. This one right there. So you'd actually end up just knocking this one out anyways, right? And so this will always match up, this middle bit. I was on eraser. This middle bit will always match up because here you have your basis is going to be in R2, in your output space, in Rn, right? In your input space. And you'll always have the two vectors that match with it because from the question, they give you two vectors, give you two statements. Right? You'll always have those two. So this will always work. Which is why, yeah? No, go for it.
So the first method that we use, that would only work if they're in the same, if it's just Rn by Rn, and this one will work for every other type of situation?
Yep. So this works for Rn to Rm. The matrix thing with where you result in In and the matrix representation of T, that is only for Rn to Rn.
Okay, cool. Thank you.
Yeah. No problem.
So wait, what is this form here actually, right? Because I don't remember this.
This here? This?
Yeah.
Well, in general, with the inverse here, right? So in general, it's what I wrote up here, right? It's this one. Here, where to find the matrix representation of, where did I go? To find the matrix representation of T, you take the output vectors, output, here, right? And you multiply them with the inverse of the input vectors. Input. That's just one of the formulas from 5.2.
Yeah, but this is they're in the same like R space, right?
They don't have to be.
Both R3. Oh, okay.
They don't have to be. The only criteria that has to be true is that these have to be a basis for Rn. Oh, sorry, not these. Sorry, just the A's. Just the A's have to form a basis for Rn. Right.
All right, cool.
So in my example here, not my example, from the textbook example, right? This and this forms a basis for R2, which is our input space, right?
Yeah.
And then we this is the output. These are the output vectors. These are the output vectors. Okay, so we actually do, any other question about that?
It's good.
From anyone else? So let's actually solve the problem now. So let's actually multiply these matrices, right? So I'll find the inverse of this one, right? So the inverse of this one is going to be 1, 0, negative 1, 1, 1, 0 times 1 over the determinant. So the determinant is 2 plus 1, so 1/3, times the adjugate of that, which is going to be 1, 2, negative 1, 1. Okay. I hope I'm allowed to move that 1/3. Usually I move the 1/3 in because I'm actually not so sure that I'm allowed to move the 1/3 here, but let's try and see if we get the right answer. If not, then this is a point where I could have made a mistake, because maybe I should multiply that in. But let's see. So this is 1, 0, negative 1, 1, 1, 0. Okay, and we're just multiplying that by 1, negative 1, 1, 2.
Wait, sorry, is this from like Cramer's rule or something?
This is from chapter 2. This is just matrix multiplication, just like doing matrix multiplication, right? And so the way I found the inverse is using this formula. So the formula is that if A is equal to A, B, C, D, then A inverse is equal to 1 over the determinant of A times the adjugate of A, which is actually for any matrix. You can just say the adjugate of A, right? But in the specific case of 2x2 matrices, it's best to you can just remember it. So it's the A and the D switch places, and the B and the C go negative.
Right. All right, thanks.
This is more complicated for 3x3 and higher, dimension matrices, but for 2x2, it's just like you can just remember this formula, and it works. I guess I shouldn't erase it, really. Although I kind of need the space, so I will erase it. Or I'll just move it to the side. Oh, boy. Okay. Decided to send me back up. Oh, did it select everything? Come on. There we go. Just move it over here. And this is a side note. Okay. And if anyone's ever done math with me, they know I cannot do matrix multiplication that well. So I do a kind of complicated way. So to multiply, I'm going to forget about the 1/3 just for a second. I won't forget it's there. But just this stuff. To multiply the matrices, well, what I do is I take this matrix and multiply with the first vector. This is how you do it. It's just that there's also much faster ways, but this is just how I'm used to it. So I know my answer is going to have 2 columns. So I say U1 is the first column and U2 is the second column. So I say U1 is going to equal the matrix, the left matrix, times the first column. And U2 is going to be the matrix on the left times the second column. And this will get you the answer. So this is 1 times that plus 1 times that, which is 1 plus 0, negative 1 plus 1, 1 plus 0. Okay. So that's the first column of my answer. And then the second column of my answer is going to be negative 1 times 1, negative 1, 1, plus 2 times 0, 1, 0. It's going to be negative 1, 1 plus 2, negative 1, and there you go. So the answer to this multiplication is, so it's going to be 1/3 times the matrix with the first column is 1, 0, 1. Right, that goes to there. I'll just draw with a little dot on top. And negative 1, 3, negative 1. Just put that there. Okay. So Now I just multiply it, right? Now I just multiply it. This is a 0. So 1/3 of this is going to be 1/3, negative 1/3, 0, 1, 1/3, negative 1/3. Okay, so that's my matrix representation of t. Let's check if that's right in the book just before I move on. So this was 7. What was this? 7.1.4b.
Yeah.
It's right?
Yeah, 7.1.4b.
Yeah, 1/3. Oh, well, they write it a little bit differently, but yeah, it is right. Yeah. And so let me actually make sure it's exactly right. Negative. Yep. X minus y. Yeah. Okay, we're good. So, this is our matrix representation of, what was the transformation called? T? Yeah, T. Right, from the original question, right? So the original question gave us, so this is where the question stops and my solution begins. So that's the question up there. So t goes from R2 to R3. We know that t does this to these two vectors, which form a basis for R2, right? So we calculated the matrix representation of t. We did that. That was our first stop. And then now we have to do t of v, where v is negative 1, 2. So to calculate t of, well, I'll just write negative 1, 2. Well, we just take this matrix, right? 1/3, negative 1/3, 0, 1, 1/3, negative 1/3, and multiply it by negative 1, 2. Right? So I get negative 1 times 1/3, 0, 1/3, plus 2 times negative 1/3, 1, negative 1/3. Right? So negative 1, negative 1/3 plus negative 1/3 minus 2/3 is negative 1. 0 plus 2 is 2. And negative 1/3 minus 2/3 is negative 1. So t of v equals negative 1 to negative 1. And question's done. Okay. So that's that question. So that's what happens when you're not going from Rn to Rn. You're going from Rn to Rm. Right? M here. And that's it for 5.2, unless anyone has any other questions.
Yeah, I have a question. Usually Rn represents like a smaller r, so is it also works for like Rm to Rn?
Let's see what it works. So we know that what we're given, right? So if we have a question like that, if we're going from a bigger, so if we're going from Rm to Rn, where m is bigger than n, right? Then we must be given enough, we must be given m vectors here, right? T equals, I'll call this, I guess I'll call it A. And this is B1. T A2 equals B2. And we must be given m of them. AM equals BM, okay? So with that, we can form the inverse matrix thing here, right? With that, we can form this. And this will be A1, A2, AN, no, AM. Right?
Is it the input on the left?
Yeah, maybe I did it wrong, did I? No, it's this is right. This is where it should go, and then this will be the output vectors. I think you're thinking of you're thinking about the augmented matrix thing, right? So definitely the augmented matrix thing won't work if they're not the same n, right? Not the, if m doesn't equal n. But in this case, this output will be a, okay, so whatever, the output will just be B1, B2, B3, no, Bn, right? And so this matrix here is going to be m by m. This is going to be m by m. And this matrix here is going to be, this is the thing here. Hold on. Yeah, so this is going to be,
Is that supposed to be BN or BM?
That's supposed to be an M here, yeah.
Okay.
And this is going to be N. Yeah, this is going to be N
Times M.
by M, right? And so
Yeah.
since this matches, we're good.
It does work.
It does work. Yeah, it does work.
It should. Okay, cool.
So we just made sure by doing this, right? But yeah, it does work.
Yeah, thanks.
Yeah, no problem.
So this would get pretty complicated if you got like T of R4 to R3.
Yeah, but it would be the same process. It would get complicated, but it would be the same process.
Okay, so that's what I'll expect on the test.
Yes. I guess that's how it is. That's how it is for us.
Could you scroll up a little bit?
Well, how far up?
Okay, so yeah, right there. So in the book they do it like in a different notation. So is it fine if we do it in like a matrix thing, or?
Yeah. So the notation
Like how
they
you
wrote in the
did it.
book is actually a little bit of a trick, right? A trick for how to write this, how to figure this out, right? So if I have a matrix that's written like this, so let's just like forget, like it's gonna be the same question, but kind of forget what we just did there. Let's just say I have a matrix that goes from R2 to R3, okay, and T of x, y is x minus y, 3y, x minus y. Yeah. Then I can immediately just take this, and try to manipulate this a little bit. First of all, I want to rewrite it as this: x minus y, 0x plus 3y, x minus y. And this is still a matrix, right? And then what I can do is I can kind of notice that this is kind of not just kind of, this is the same thing as, this is x times 1, 0, 1 plus y times -1, 3, -1. So try to think about it and try to notice that these are the same thing. And this is just matrix vector multiplication. -1. Right? X, y. But look at this. This is in the form ax. And we said that t of x can be written as ax. Well, A is the matrix representation of T. And so all they did in the question is they expected you to go from this. This is what we said, except multiplied by 3. The fact that it doesn't make a difference. Well, if you multiply standard basis vectors by 3, it doesn't actually make a difference. Sorry, it's divided by 3. So see, this is our answer for the last one was 1, -1, 0, 3, 1, -1 times a third. And I got the same thing. 1, -1, 0, 3, 1, -1. Not times a third, but that again, that doesn't matter because it's the standard basis vectors are, if you have this vector and this vector that are a basis for for Rn, or for R2 in this case, R2, it doesn't matter if you scale this either vector by any amount except 0, right? So if I just decide I want this vector to be twice as long, it doesn't change anything, right? Or if I decide I want it to be half as long or a third as long, it still doesn't change the span of these two vectors. There's still a basis for R2. If I made it multiply by 0, then yes, that would change things. Right, scaled it by 0.
Could negative values also work?
Yeah, right. So
yeah,
right. If I start like this, but then I just decide it wants to be like that, it's still a basis for R2, right?
Yeah.
So that's why it doesn't matter here that the third is different. It's the same transformation that's happening. Right? And so notice this is just another way to find the matrix representation, right? But this is the reason I didn't do this originally is because I got this from the answer. This statement here, that's the answer to the last question, is pretty much this. Written again, kind of a weird way, but it's pretty much just saying this. And so you can work backwards from this, right? If maybe, for example, the question gave you this, like they defined T in terms of this, you can create a matrix where all the columns are T of E1, T of E2, ... T of En. and you will get the exact same answer as if you just looked at this and just turned it into a matrix of like doing these steps, right? Noticing that it's a linear combination of x and y matrix, you'll get the same answer. And to do it fast, I could look at this and just say, well, think about how many x's we have in each column. So in each row, sorry. So we have an x here, so 1. We have no x here, so it's a 0. Similarly, we have an x there, so it's a 1. Now think about the y's. We have negative 1 y's there, 3 y's there, negative 1 y's there. And again, we get the matrix representation of t. So
wait, what were you trying to prove with the T of E1 and E2?
That's how we did it in 5.1. So in 5.1, it says to find the matrix representation of t, you apply, or no, that's actually the beginning of 5.2, is to find the matrix representation of t, right? You apply t, this transformation, to each of the basis vectors.
Yeah, okay.
Right? Which would get you the same answer as doing this, which would get you the same answer as doing this whole thing that I did originally.
Yeah, okay.
Right? It's just the same transformation. Which would get you the same answer as if, for example, if they just gave you this. It's all the same question, right? It's the same transformation. So if they just gave you this, right, and doing all these steps, you'd get the same answer. It just depends on what they give you. Right? So we did that too.
Yeah.
Okay, guys, so it's 7:30, so let's take our 15-minute break, and then I'll start 5.3 right after the break. Okay?
Oh, so we're on 5.2. Okay, I was about to ask where we were.
Yeah, so we're right at the end of 5.2, so we'll start 5.3 next time, after the break. Okay.
Can you go back up to the last thing that you were doing, the last question? The answer. I just want to look at that. No, not this one.
The answer to the question, yeah.
Yeah. This
T of
one?
V.
Okay, thank you so much.
T of V is there, and then the matrix representation is that up here.
Okay, I got the answer. Thank you.
Good, no problem. Okay, so I will go on AFK. Boom. And I will change that time to 47. There. Okay, so I'll be back at 7:47. So hope to see you guys all after. Okay. Okay, hi guys. I'm back.
Yeah.
Change the camera. My favorite transitions. We're good. Okay, so someone say something that I couldn't hear.
No. Is this the most amount of people we've had since Death Form?
Well, it's most amount of people for a while. Yeah, it hasn't been more than I mean, obviously never more than 50, but we haven't hit the cap for a while. So, yeah. So I'm happy lots of people here. And for anybody who, obviously I know everybody I'm speaking to is in the call, but anybody who misses it and is asking what they should do, well, I mean, this is recorded, so it'll be posted right after. And yeah, so good. Okay, so let's move on. I have opened the textbook. Linear Algebra. Okay, so 5.3 is called Properties of Linear Transformations. Yeah, okay, this is a good question. I think, yeah. Let me find. So this chapter is gonna talk about composite functions and composite transformations, inverse transformations, and that's it. Composite transformations and inverse transformations. And one question which I think we should do here, which is from the textbook. But other than that, it's just those two things. Okay, so 5.3 now. Okay, so this example from the textbook is not related to the two things I just said, but it is useful to know. It is a property of linear transformation, which is what 5.3 is, right? So the question is that what the question gives us is T goes from R3 to R4, okay? It's a linear transformation such that T of 1, 3, 1 equals 4, 4, 0, negative 2. 4, 4, 0, negative 2. Right? And T of 4, 0, 5 equals 4, 5, negative 1, 5. Okay, 4, 5, negative 1. Can't write. Okay. We can't, and the question is find T of negative 7, 3, negative 9. That's the question. Find T of negative 7, 3, negative 9. So, right off the bat, do we have a definition for T that lets us right away create a matrix? No. That would be like having T of XYZ equals X something, Y something, Z something. We don't have that. Okay, can I do this thing? A inverse B. I can't. Because this and this do not form a basis for R3. So I can't do that either. So only thing I can do is try to see if I can create this vector, or create this whole thing, as a combination of these two. Right? So in other words, we want to see if I can create negative 7, 3, negative 9 as a combination of 1, 3, 1 and 4, 0, 5. Right? We're trying to see if this has any solutions for A and B. So let's do that. Let's try to see if that does exist. Okay, so I'll put these two into a matrix. Right, I moved my hand up as if I was going to squish it, but yeah. Put this into a matrix, augment it with this. 1, 3, 1, 4, 0, 5, augmented with negative 7, 3, negative 9. Okay, put this in RREF. I might just, how about I just, for the sake of just keeping it short, the solution has the RREF right here. So after RREF, it looks like this. 1, 0, 0, 1, 0, 0, 1, negative 2, 0. Okay, and so the solutions for A and B are A equals 1, B equals negative 2. Okay. So, since we know that negative 7, 3, -9, that vector, equals 1 times this one, 1, 3, 1, minus 2 times this one, 4, 0, 5. Let's take t of both sides. So t of -7, 3, -9, which is what we're looking for, right? That's what the question asks us to do. Find that. Is equal to t of 1 times, and I won't even write the 1 times because there's no point. 1, 3, 1 minus 2 times 4, 0, 5. But remember, this is a linear transformation. One of the important properties of a linear transformation is that it distributes over addition, and you can factor out the linear, the scalar. Sorry, I can't say the right words. So it distributes over addition, and you can factor out the scalar. So we can write, and I'll just write an equal sign here, right? Because that's equal to that. That's equal to t of 1, 3, 1 minus 2 times t of 4, 0, 5. We know these things from the question. We know what t of 1, 3, 1 is. We know what t of 4, 0, 5 is. So t of 1, 3, 1 is 4, 4, 0, -2. -2, yep. Minus 2 times t of 4, 0, 5. Well, t of 4, 0, 5 is 4, 5, -1, 5. And these two vectors we know from the question. Okay, so 4 minus 8 is -4. 4 minus 10 is -6. And 0 plus 2 is 2. And -2 minus 10 is -12. And that's the answer. That is t of -7, 3, -9. Okay, so that's that question. And so any questions about this? Any questions about this?
Yeah, how is this different from 5.2?
How would I what? Sorry?
How is this different from 5.2? Like, what's the difference? And did you say that the inputs weren't in R3?
Yeah, this wouldn't work because the inputs don't form a basis for R3. Right? They're in R3, but they don't form a basis for R3.
Okay.
Right? This set 1, 3, 1 and 4, 0, 5 is not a basis for R3. They're both in R3, right? But not basis. Basis for R3. So you can't use this. You can't use this method because the criteria for using that method is that the input space has to be a basis for your input space, right? The input matrix has to be a basis for your input space.
Yeah.
So the reason this is different is because we can't use that method. So we have to express this goal vector as a linear combination of these two. If you can't do that, I don't think there's a way to do this. Because you just don't have enough information about the question. Yeah, go for it.
Where'd the free variable go? Because when you did the REF, there's a 0 column. Or a 0 row, I mean.
There's a 0 row, but no 0 column, right? So
So what does that mean in this situation?
It means that there's no like if well, it doesn't mean I have a free variable. There's no free variable, right? No free variable, right? Because the free variable would be a column if you had a column without a leading entry, right? All the 0 does is it's pretty much just saying we don't have a C we're solving for. We're not solving for any kind of C value, right? I only had 2 vectors, right? So if I was trying to make this as a linear combination of 3 vectors, well then Then I'd need another vector here, right? Then I would have a C value. Then I'd have another column here, stuck in here, right? And I would get a 1 on the bottom there. And so I'd solve for C as well.
Right.
But since
So
I
you would
don't,
need
since I
like
don't have that.
you need a third transformation in order to do that.
A third basis vector. You need a third basis
Yeah.
vector. Yeah. And if you had that, then you wouldn't have to do all this. You could just do this. Right?
But wouldn't it be easier to go with this? Because like doing the and all that is.
Yeah, it would work. Yeah, and I guess it would be easier. Let me think. But what would you get from? Sorry. This is not going to get you the answer. This is going to get you the matrix representation of T. So if that's what you're looking for, this method doesn't get you the matrix representation of T. It just gets you T evaluated at some vector.
Oh, okay.
Right? So that's not what we're getting with this question. We were just getting T evaluated at that vector.
Right. The reason that the two input values weren't in basis is because we need a third one. Then we could use it.
Yeah. If you had 3 input vectors and they were all linearly independent, then they would form a basis for R3.
Yeah.
Then they would form a basis.
Could you scroll down to the part where you like substitute?
Yeah, here, right? So I know T of 131 is this. It gives it to me in the question. I know T of 405 is this. It gives it to me in the question.
Okay, yeah, I completely forgot about that part. And could you go back up? So I'm just like a little confused as to why it's not like a basis, like for R3.
Well, so imagine, let's take it to R2. Let's take it to R2. I'm in R2. I have a flat plane, and I have one basis vector. Right? Does that form? Is the span of this vector? Is that all of R2? The span of this one vector, as in all the linear combinations of this vector. Well, they just form a line. All the possible linear combinations just form a line. So if we're in R2, and we have a set which just contains one vector, then it is not a basis for R2. Right? But if we were in R2 and we had 2 vectors, any 2 vectors that are linearly independent, then yeah, the span of these 2 vectors is all of R2. Any point here, any point in R2, I can describe as a linear combination of this vector plus this vector, which is what it means to span R2, is that any point in R2 can be written as a linear combination of the basis vectors. So taking this to R3, if we're in 3-dimensional space and I only have 2 basis vectors, then I'm just describing a plane. I'm just describing a plane in R3, right? It's not all of R3. It's just a plane in R3. It's just a flat slice. Maybe I can show a picture. No, I'm not that lucky. Well, like kind of just this, right? Kind of just. So this isn't that descriptive, but we're in R3, and each of these planes has 2 basis vectors. Just the planes, they have 2 basis vectors, right? The green one is going to could look like that. That could be the basis, right, for the green one. And so any point on that plane can be described as a combination of A and B, these 2 vectors, right? But all of R3, like if I wanted to do this point over here, that's like away from the graph, right? Away from the plane, I mean. There's no way I can describe that point as a combination of these 2 vectors. So it doesn't span all of R3. Right?
Okay, that makes sense. Thank you.
Which is why this doesn't span all of R3. This is just describing some plane in R3. Right?
Yeah. Okay, I get it.
Good. Sounds good.
I have a question. Now that you have the value for the transformation of T on that vector, would you be able to find the matrix T?
Very, very good question. I was hoping someone would ask that exact question because I was thinking I have a good answer for it. So the answer is no, because this vector, right? So to be able to do that, you have to do this. You'd have to do this, right? And the criteria for that is that the input space is linearly independent. So you would use this, and then our answer from this one, right? The problem is that set, these yellow vectors, 1, 3, 1, 1, 3, 1, 405, and our answer that we got, or not the answer, but the input of the answer, is also not a basis for R3. Not a basis, which is the criteria for doing that B A inverse. The input space has to be a basis. The reason it's not a basis is because we use this in the question, that this is a linear combination of these two.
Okay. Yeah, I get it.
Right? That's a linear combination. So it is, so this doesn't add anything to the span. So it's a dependency. It's a linear dependency. So you would take it out to form a linearly deep independent set. Right?
Okay, I get it.
Right. So it's not a basis for R3. So we still don't know more about the transformation at all. Right? We don't know anything else about the transformation. Okay, any other questions about this question?
Oh, we just used the fact that it's a combination of the other two, and then use the scaling and just did it.
Exactly. Yeah. That's right. Yeah. Which is why it's not independent in this set, because we use the fact that it's a combination to solve the problem.
We still technically haven't found the matrix representation of T.
No, we haven't. And I don't think, well, could we? Yeah, we probably could somehow. Let me think how. No, could we?
Let's not.
I don't know how you would. You'd have to see if this. No, but that doesn't make sense. You'd have to see if somehow. No, it won't. It wouldn't work. It wouldn't work. Never mind. So the way that I'm thinking, it wouldn't work. So maybe there's a way. I just don't know.
Yeah.
Right. So yeah. Okay. So yeah, there's that question. Let's move on to what 5.3 is like. That's what 5.3. This is part of 5.3, but the important part is that if we have a transformation T, right in black, T, which goes from Rk to Rn, we have a transformation S that goes from Rn to Rm. Then you can define the composite of these two, S of T, to be Rk goes to Rm. Right? And these are the same two. So a composite function. One transformation after another. That's pretty much all it is. Right? And this is identical to saying S of T of X. Just like a function, right? Just like a function. And another important thing to notice is that you apply the inside function to X first, just like you do with functions, and then you apply the outside function. It's a little more something you can make a mistake on here, where you'd apply the outside function first or something like that, right? So if you think about it, right, if T is a transformation, S is another transformation, right? Then if I take a vector and I want to apply T first, then I would multiply it by the matrix representation of T. And assuming that, again, T goes from Rk to Rn, and this one goes from Rn to Rm, assuming this matches up, then I can just apply the matrix representation of S to that, right? As a vector X, right? And so a little bit of a simpler way of writing it is just without the bracket, is that S of T, here I'll write S of T of X is equal to, yeah, let me get this right, hold on. Yeah, I think that's right, okay. Matrix representation of T Yeah, and then the matrix representation of S times X. And if you wanted the matrix representation just of S of t, then you could multiply these together. And that would make the matrix representation of S of t. And there'll be just one matrix instead of two. But it's the same idea, right? It's the same multiplying the matrix idea. Multiplying the vector idea. You wouldn't be able to switch them. Because if you switch them, you'd be going from Rn to Rm, and then from Rk to Rn. This doesn't match up, so there's no way. It's not in the domain. Right?
So, like, just to clarify, I'm still not really clear. Like, just because it goes from k to n and then n to m, then we can just multiply both of the matrix representations.
Yeah, because they're composite functions. They're composite functions, yeah.
Oh, okay.
Yeah, that's right. Yeah. It's important that they go from this middle bit is the same n, right? Because just like if you did f of g of x, right? The output from g of x, right? The output from g of x has to be in the domain of f of x. Otherwise, this doesn't do anything.
Yeah. So wait, are you saying that it's from like t moves Rk to Rn, and then that R is moved from n to m with S?
Mm-hmm.
Or is it two different things right there?
No, those are two different transformations. Those are two separate transformations. One goes from Rk to Rn. K, N, and M could be all the same. They could be all R2, 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 right? But it doesn't really matter, but you could, as long as those middle ones match up, right? Because, yeah, so one transformation takes everything from Rk into Rn, right? And the second transformation will take everything from Rn into Rm, some other dimension.
Right? Yeah.
And as long as those middle two match up, it'll be possible. It'll be possible to do.
Yeah.
Okay, so that's that. Let's see an example. This isn't too crazy, but I'll just do one example here. Unless there's a nice example in this. T of S is T times S. F 2x by x plus. Yeah, let's do this one. I like this one better. Okay, let's do this. Yeah. So here's our example. Example S is a transformation from R. Did I write? S is a transformation from R2 to R2. And defined like this. So S of xy is equal to x plus y, x minus y, right? T is a transformation from R2 to R2. S of xy, t of xy is equal to 2y minus x. And so our goal for the question is to find the matrix representation of T of S. That's it, actually. So find the matrix representation. What'd you say? Sorry?
I can't actually see what S is equal to at your...
Oh, sorry. There you go.
Yeah. Okay. Thanks.
No problem. Sorry about that.
Yeah.
Okay, so S is x plus y, x minus y, T is 2y minus x. Okay, so our goal is to find T of S. So in Horowitz, there's two ways here. Either are pretty good, honestly. Yeah. So what this is going to look like is it's going to look like the matrix representation of T times the matrix representation of S. I should have said it the other way. The matrix representation of S times the matrix representation of T. Right? So it's important the order stays right here. Right? So first of all, we can find the matrix representation of S actually pretty quickly from this. Right? We can use that trick I said, right? So I can just treat this like 1x plus 1y, 1x minus 1y. Notice that this looks like matrix multiplication, matrix vector multiplication. So x, so 1 there, sorry. X 1, 1 plus y 1 minus 1. And that this ends up being the matrix representation of S. Okay, so that's the matrix representation of S. And for a very similar reason, the matrix representation of, oh, that doesn't make sense. No, that does make sense. Yeah. Sorry. Wait, what did I do here? Yeah. Okay, sorry. So the matrix representation of this would be 0, -1. There's no x's, there's 2 y's, and 0. There you go. Okay, sorry, I got confused there. The matrix representation of that would be that, and the matrix representation of S would be that. So we can actually just multiply them now, right? So if the matrix representation of T is 0, 2, -1, 0, I'm going to multiply that on the right by the matrix representation of S, which was 1, 1, 1, -1. I can just multiply, and this will give me the answer, right? So again, I multiply weird, so I know my answer is going to have 2 columns. So column 1 is going to be 0, 2, -1, 0 times 1, 1, which is going to be 1 times 0, -1 plus 1 times 2, 0, which is 0 plus 2, -1 plus 0. Okay, that's my first column. And my second column will be 0, 2, -1, 0, this matrix, times the second column, 1, -1. Right, which is going to be 1 times 0, -1, minus 1 times 2, 0. So 0 minus 2, -1 minus 0. Okay. And so, yep. And so the matrix representation of S of T? No, T of S. T of S equals column 1, 2, -1, -2, -1. Yeah, that's right.
Quick question. When can you make that shortcut assumption?
What's the shortcut assumption?
That first one where you said 1x plus 1y and then 1x minus 1y. When can you make that assumption?
Whenever you see a transformation defined like that. Defined by like S of xy equals this, something happening to x and y. Or like that. If you have the general transformation, right? Just like if you had f of x, right? You know, you can find, well, I mean, it's a little bit different with functions, right? But you can find all the coefficients of all the things, right? Because you have it. It's 2x plus 3 or whatever the function is, right? So same way here, you can find the matrix. Since you have the general form, you can find the matrix.
Okay,
right?
cool.
Same
Thank you.
Same with T. No problem.
Can you scroll down? You have like, is it multiplication right here? Wouldn't it be 0, 2 times like that last line? The last line.
Yeah, here I did this times this here.
Oh yeah, sorry.
Right, this times this here, and then I did this times this here.
Got you. Thanks.
Make sense? Okay.
Yeah.
Good.
Could you explain the shortcut thingy one more time?
With this up here?
Yeah, just one more time.
For sure. So, well, I don't know what that is. That just shows up for some reason on my screen sometimes. Okay, so I'll just copy this and I'll move it down. So all I'm doing is I'm pretty much writing this matrix. I have to restart OneNote, sorry guys. There. Okay. There you go. Okay. So I'm pretty much writing this matrix, right? This matrix as a linear combination of x and y, right? So what would that be as a linear combination of x and y as variables, right? So not the matrix is an x and y, but the variables are x and y. Well, I have 1, 1, right? There's an x in both of them, and it's 1, -1. right? And so that 1, 1, 1, negative 1 is my matrix representation of S, right? Same thing here. I'm writing this as a linear combination of X and Y. So it would be 0, negative 1, 2, 0. So what I get from that is 0, negative 1, 2, 0 is my matrix representation of T. Does that make sense? Hopefully. Okay, definition T. Okay, so the next part is an inverse transformation. It's pretty much if you have a composite, if you have T that goes from Rn to Rm, and you have S that goes from Rm to Rn, right? You say that T equals S inverse, or sorry, you say that S equals T inverse, right? S equals T, I think that's maybe what I just wrote, and yeah, anyways. You can say S is T inverse if and only if, right? T of S of X gets you X, and S of T of X also gets you X. As in, the T of S and S of T cancel each other out. So S equals T inverse, and T equals S inverse. Right? And so here's a few important points. So if T is linear, then S and then T inverse exists. And to calculate the matrix representation of T inverse, well, you just take, if you have the matrix representation of T, you just take the inverse of that. That's why we learn matrix inverses, right? Like, I mean, there's other applications to it too, but that's like what it actually geometrically is well, algebraically really, but hopefully you can visualize it a little bit, is that like T is the transformation that takes the basis vectors from here to whatever, to lines them like that, right? And so that's T, and T inverse would you bring you from that to that. Right, that's what T inverse is. Okay, so let's find an inverse. So example, T of x, y equals x plus y, x minus y. Okay, I want T inverse. So I'll take the matrix representation of this, 1, 1, 1, 1. Well, I'll do it like this, 1, 1, 1, negative 1. Right, so that's for your x's, that's for your y's. Right? And then I want the inverse of this. To find T inverse, I just take so that's the matrix representation of T. Right? So the matrix representation of T inverse, or T inverse should be in there, is 1, 1, 1, negative 1, inverse. So that's 1 over the determinant, negative 1 minus 1, so negative a half, times the adjugate. So negative 1, 1, negative 1, negative 1. Okay, and that's our answer. I mean, maybe I'll move the negative in, so 1, 1, 1, negative 1, and there you go. Yeah. And that's our answer. Let's just make sure that's right. Yeah, there you go. That's correct. Okay, and then that's all of 5.3. So if you have any other questions from 5.3, let me know now. The inverse is unique. It's another important point, but not too helpful really, but just an important point. Yeah, that's it. That's all of 5.3. So, unless there's any other questions, I'll move on to 5.4. I'll open the chat, see if anyone's saying anything. So let's move on to 5.4. So 5.4 is called special linear transformations. So a specific couple that we're going to talk about in R2 and in R3. So the first important one is R theta. Okay, R theta. So not R theta like R theta, like as in the like a Rn or something like that. No, R theta as in that's a transformation, right? Oh, which goes from R2 to R2, and all it does is it takes. So if I say yeah, I'll just do like this. So if I have a vector like this, right? Just a not a basis vector, just a vector. And it transforms it so that every vector in R2 is rotated clockwise by theta. So we'll end up like that. Okay, so R theta. And so how you'd write the matrix representation of R theta is this. So it's cos theta negative sine theta, sine theta cos theta. And so that's it. That's the matrix representation of R. So if I wanted to apply that to this vector right here, I'd write that vector as 1, 0. And let's say I'd have to pick a theta, right? So let's actually do it here. I'll pick a theta. I want it to go upright. So I want theta to be pi over 2. So R pi over 2 is going to be cos pi over 2. I'm very bad at remembering all the things, so I will just put it here. Cos pi by 2 is a 0, I think. Yeah. So 0. Oh, sorry, I'm getting a phone call, so I can't hear if someone's talking. One second, guys. Sorry. Let me make sure that this is working. Yes, I was watching 3 Blue 1 Brown. Okay, just making sure my audio is working. Okay, good. So, can someone say something? Make sure I hear them. Make sure I can still hear the chat.
How'd you get negative 9 theta?
So this is a rule. This is just a formula. This is just a formula to memorize, right?
Oh, okay.
If you want an explanation as to why, then look at this picture. This picture will kind of explain why. If you kind of have to understand how polar coordinates work, but so if you start like your basis, if your basis was here, E1, ended up here, then its new coordinates would be cos theta sine theta. That's the that's a polar coordinate kind of thing. This is kind of like a more advanced trig, but yeah. So the coordinates would be cos theta sine theta, and so that's why you put it in that's why it's the first column here, right? Cos theta sine theta. And the coordinates of this would be negative sine theta cos theta, which is why this is negative sine theta cos theta.
Got you.
Okay, so that's why, yeah. So cos of pi over 2 is 0, cos of pi over 2 is 0, sine of pi over 2 is 1, I'm pretty sure, but I will check because, again, I am bad at remembering, is 1, so we put negative 1 here and 1 there. So ideally, if I multiply this vector, which is 1, 0, by this, I'm expecting that I will get 0, 1. And let's see if that's right. Right? So multiplying this would be 1, 0, 1 plus, or I guess minus 1, minus, oh, well, never mind, sorry. 1, 0, 1 plus 0 times negative 1, 0. Right? Which is just 0, 1. Which is what I was expecting. Right? To be upright like that. So you see how it does rotate by that amount clockwise. Okay, so that's that special transformation. If you were to apply one rotation with another, it's not too complicated. You just got to know which one you got to do first, right? So if you have, like, if it asks the question, says, okay, so rotate by pi over 2, then by pi over 6, well, then you do and watch the order here, you'd first do r pi over 2, right? So if you have some vector x, pi over 2, and then you do r pi over 6. Because remember, the transformations go like this. This applies first, and then this applies to that. So you got to write it in this order. And it, well, I guess it wouldn't be different it wouldn't be different in this case, but yeah, so it wouldn't make a difference because it's additive, but it's just good to always keep that in mind when you're doing transformation, because sometimes it does matter. It doesn't matter in this case again, but sometimes it does matter, and this will trip you up. So it's good to just keep it in mind. And there's a way to derive the double angle formulas, or no, sum of angle formulas. But you don't have to worry about that with this. Yep, that's pretty much it. Okay, and then so if you want to, let's say you're in R3 now. So this is an R2, right? This is just R2, this stuff. Now let's say I want to define another function, R sub, what do I call it? R sub a theta. And what this does is it's an R3, okay, and it rotates all vectors around the a axis by theta. So a can be either x, y, z, right? So there's three options: r x theta, r y theta, and r z theta, right? This rotates, I'll type it. So this is rotate around the x-axis by theta. This one is rotate around the y-axis by theta. And this one is rotate around the z-axis by theta. Right? And there's those three. So let's do an example. Let's say I want to use it. Oh, sorry, I didn't actually I didn't show the formulas for it though. So this is equal to, the matrix representation of that is equal to, for x it's 1, 0, 0, 0, 0, and in the middle here we have cos theta, negative sine theta, cos theta. So that's the formula for that. To rotate around the x-axis by theta. To rotate around the y-axis by theta, it is this. So it is, I'm going to run cos theta, 0, negative sine theta, 0, 1, 0, sine theta, 0, cos theta. And finally for this one, for rotate around the z-axis by theta, it is cos theta, negative sine theta, cos theta. And here we have 0, 0, 1, 0, 0 along the sides. Okay, so that's...
Sorry, could you just keep it like that? So I can copy this down.
Yeah. So yeah, I'll take just a moment. Some people might be ready.
So are we just supposed to memorize this, or like how would we use this on a test? I don't know.
Yeah, if they ask you to do it, then I guess they expect you to memorize it if you're not allowed to use the notes. If they ask you to do this, right? Although he didn't make a big deal of memorizing. What'd you say?
Do you think they would like have a question on something like this? Because it's mostly just like angles and stuff. I don't see the correlation between this and like everything else we learned.
Well, it's a transformation still, right? It's a linear transformation. It right? So
isn't it like rotation?
It's a rotation, but that's still a linear transformation, the same way that we've been talking about linear transformations this whole time. Right? Right? So it'll still do the same thing. It's just a specific one that does a rotation around some axis.
Oh, okay. Right? Yeah. Alright, well, hope they don't
Gotta hope for it, I guess. Yeah.
I have a
What'd you say? Sorry.
So just memorize it.
Just memorize it, I guess. That's all. That's all there is.
I have a textbook question, but we can do it after.
For 5.4.
Yeah.
So how about let's just finish 5.4 like the content, and then we'll do it right after at the end. Okay.
Yeah.
So okay, am I good to move on from this?
Yeah, you can. I have the last one in my head. Thank you.
So the next important thing from this section is QM. Okay, it's a different transformation. QM is a reflection. It's an R2 to R2. Does it have to be an R2 to R2? I think it does. So QM, which goes from R2 to R2, right? It is a reflection through the line y equals mx. Y equals mx. There you go. Write it a little nicer. Y equals mx. So it's that reflection. And it's defined like this. So the matrix representation of QM is 1 over 1 plus m squared times 1 minus m squared, 2m, m squared minus 1. So if I want to go across the line, y equals 5x, I mean, sorry, y equals 5x, then I would just put 5 in for all the m's here. And that would be my matrix representation. There's a couple special ones, right? So what if I wanted to do the y-axis? Well, that's kind of like a slope of infinity, right? If a slope of 5, slope of 100, whatever. Slope of infinity is just the y-axis. So there's just you can't really plug it in, but you can just put q infinity, which is equal to -1, 0, 0, 1. Similarly, although this one is possible to plug in, what if you wanted to go across the x-axis? You could just plug in 0 here, and you would get q0 equals 1, 0, 0, negative.
Yeah, this is all in R2, right?
This is all in R2, yeah.
Okay. This is 5.4, right?
This is 5.4. Yep, that's right.
Okay.
Wait, so how would this work in like R3? Is this just like a formula, like a set formula?
It doesn't work in R3, so this only works in R2. Right?
So you can't reflect across the Y, across the Z, I mean.
No, like this is just like, because notice this is a 2x2 matrix, so it's only defined in R2. This process, QM, Q sub M, is only defined in R2.
So we just memorize this formula for us for reflection.
I guess so. Yep.
All right.
Okay, and then let's do an example. I think let's just do the most complicated example I can find that combines everything. So to do an example of this, we'll say calculate the matrix representation of r sub theta, so r sub pi over 4, theta equals pi over 4, composed with q1. Okay, so to do this, well, I'm going to have to take the matrix representation of r pi over 4 and multiply that with q1. Matrix representation of q1. Yeah. I also just want to mention something. You could do this the way we said before, which is that since we're going from R2 to R2, so how we did it in 5.2 or 5.1 or something like that was you just apply this. Let's call that t. You just apply that to all the basis vectors. And in this case, it would just be 2 basis vectors. I just want to make it clear that that still works. You can do that. Right? That would do the same thing.
You see, like we have earlier, like if you scroll up, like with the x-axis, y-axis, or z-axis.
Mm-hmm.
Yeah. So when you just have r pi over 4, which one would you use it? Or could you basically use any one of them?
You'd use this formula up here. This one. None of those. Those are all defined in R3. This is the one defined in R2. You use this formula, right?
How do you know this is R2?
Because these transformations are only defined in R2.
Oh, okay.
They're only defined in R2. R sub A comma theta, that's in R3. But just R sub theta, that's R2. Q sub M is just R2. So there's no way that this is anything except R2. Even though it doesn't say in the question, there's just no way that it's anything else. Right? So let's see here. So if I want the matrix representation of this, well, again, so I can do either this or I can do this. I'll do this because it is like, this is actually pretty complicated if you think about it, right? So I'll have to apply Q1 to this and then apply R pi over 4 to that. Like, it's not crazy, but it's a little bit more complicated than I'd like. So this will get the job done nicer. So R theta. So remember, R theta is, well, I won't write the general one. R pi over 4 is going to be cosine pi over 4 minus sine pi over 4, sine pi over 4, cosine pi over 4. And I'm going to multiply that by Q1. And Q1, I need a little space there because it's going to be, the formula was 1 over 1 plus 1 squared. So that's m, right? But m is 1 in this case, so 1 plus 1 squared. 1 minus 1 squared, 2 times 1, 2 times 1, 1 squared minus 1. Okay, so I'm going to move that 1/2 to the front, right? So it's 1/2 times cosine of pi over 4. I think that's a bunch of root 2's. No. Oh, he changed the question in the middle of it, so that's why I didn't notice. He changed the question in the middle of it. Instead of Q1, he did. Yeah, actually, let's do the different one because I would want it to be more complicated. So instead of Q1, well, should I do it? Because it's kind of annoying to do. Never mind. I'm not going to do it. So let's just keep going like this. So what's cosine of pi over 4 is root 2 over 2. So root 2 over 2.
I think they're all root 2 over 2.
Yeah, I think so too. Yep. So minus root 2 over 2, root 2 over 2, root 2 over 2. Okay. And then this matrix is going to be 1 minus 1. 2, 2, 1 minus 1. I hope I'm allowed to do this. Let's check. Well, actually, I can't even check because I don't know the answer. So maybe I shouldn't. I was thinking I'd factor out a 2 from this. Yeah, I think I can do that. And I can just write this as root 2, root 2 over 2 minus root 2 over 2, root 2 over 2, root 2 over 2 times 0, 1, 1, 0. I think that'll work. Yeah. Again, I can't really check, so that's kind of going to make me nervous, but we'll see. So anyway, so this multiplication will have 2 columns. U1 is going to be, I really don't want to write this a million times, so I'll just copy and paste this. So it's going to be that times 0, 1. Okay, which is going to be 0 times that, and then 1 times that, so it's going to be negative root 2 over 2, root 2 over 2. And similarly, this is U2 is going to be that times 1, 0. So it's just going to be, so that times times 1, 0, which is going to be root 2 over 2, root 2 over 2. So the matrix representation of R theta, R pi over 4 composed with Q1 is negative root 2 over 2, root 2 over 2, root 2 over 2, root 2 over 2. Which, of course, I can write nicer as root 2 over 2 times negative 1, 1, 1, 1. And there's our answer. Okay.
Sorry, could you just scroll up one more time to like Q of infinity or Q infinity?
Q infinity here.
Okay. Thank you. That's fine.
No problem.
So is that like the most complicated it'll get? Because it doesn't seem like you can really do anything crazy stupid with these.
Well, M could be something weird. So this was just Q1. That's the only difference. Then you just plug in the number, but it's not really much more complicated than that. Like you just plug in the number into here, solve for the matrix. That's the only thing.
Or it's Q to a quadratic function or something.
Yeah, no, they're not gonna give us anything that weird in that denominator. They could, but
it's formats we're talking.
Yeah, so we'll see. But yeah, no, I doubt that. So
is Q always given to us?
Yo.
Hold on. Someone said Q is Q always given to us? It depends on the question, right? So if it's like if it tells you to reflect across some line, then that's what Q1 does. Or sorry, QM does. So it says, remember, QM is defined as reflection through the line y equals mx. So whenever it asks you to do that, it's giving you that.
Oh, I see. Okay.
Okay, and someone else.
When would we be using the Q infinity?
If y-axis. This reflects over the y-axis, right? Because a line with slope infinity is a vertical line.
Okay, yeah.
Right? So if it ever asks you to reflect across the y-axis, that's what Q infinity is. Q infinity is...
Oh, so you just use this matrix presentation.
Yeah, yeah. Reflect across y-axis. That's that. And this is reflect across x-axis. Yeah.
For some reason, Q infinity and Q0 are like the adjutants of each other.
Sorry, what did you say? Q infinity, Q0? What was that?
Each other. That's just...
They add to each other?
Edge of each other.
Oh, yes. Oh, yes. They're just the... It looks like it. I mean, there would be... Flip those and yeah. Well, it also kind of makes sense if you think about if you think about how this would work if I multiplied some vector a, b here, right? Well, it would just be, all it would be doing is changing the sign of the x value, right? It would just be multiplying the x value by -1, which is just what it is to reflect across the y-axis. Similar for this here, right? So,
yeah.
Could we also, in order to find that Q, like if it has a reflection in the y-axis, we can also multiply all our x values by -1. And if there's a reflection in the x-axis, could we multiply all our y values by -1?
That's exactly what these matrices are doing. That's exactly what these matrices are doing. This is reflecting all the x values by -1 for the y-axis, reflecting all the all the y values by -1 to reflect over across the x-axis.
And okay, and then the only extra part is that you can have a different Q subscript.
But if it tells you to across the y-axis, it's Q infinity, right? If it tells you across the x-axis, it's Q0, right?
Okay, because that's all I've ever encountered. I've never encountered it where I have to use that formula 1 over 1 plus 1 squared.
If it asked you reflect, well, that's what we did in this question right here. It said reflect over y equals 1x, right? That line, that straight line. So that would be this here.
Okay.
Plugging it into the formula with M.
What's this called when you with the Q's?
Let's look at the textbook.
Because I don't remember seeing this in my class.
Rotation here. Reflection. QM, linear transformation given by reflecting. Yeah.
Okay. All right. Thank you.
That's all it is in textbook. Yeah. No problem. Maybe it has it at the start. Let's see.
I see that it says like reflection in R2. Is it different?
Let's see.
Because is it reflection in R2?
Where? Oh, I gotta find it again.
Theorem 5.2.
I lost it. Yeah. Here.
Yeah.
What was it? Sorry. What did you say?
they have reflection, but then they have reflection in R2. Is there like could it go like onto like N? Like hypothetical.
Well, it's just that it gets more complicated to define a line in Rn, right? In
Yeah,
R2, you
right.
just need the m value. That's all you need. You just need the m value of the line, right?
And in
Technically a b value, but
in R3 and it was those other 3x3 vectors.
yeah, well, exactly. In R3 and R4 and Rn, right? You just need more things to define a line. You need to give it more direction, right? And so there isn't just like a nice formula like this for reflection over. I mean, maybe there is, but we don't know it yet. They didn't teach it to us, right? So there isn't just a nice formula like that for just that, right?
All right, cool.
Okay, good. Okay, someone asked for a question, homework question.
Yeah, me.
Yes.
It's in Nicholson.
Okay.
2.68.
2.6.8?
Yeah, 2.6.8 D.
2.6.8. So 2.6.8 is, in each case, show that T is either a reflection in a line or a rotation through an angle, and find the line or angle. And D. D is here. This one?
Yeah.
Okay. So what we're trying to do is that we're trying to show that this transformation, even though we don't know it just by looking at it, is actually some combination of r theta and qm. Might be just one of them. Might be just r. Might be just m. Might be just r. Might be just q. Could be both. Probably not both. So, because that's just like a harder question. So.
Can you please go back to the question for 1 second?
Yes. So it's kind of broken up. So the actual numbers are here, but the words of the question are down here.
Okay. All right, thanks.
Good. Okay. So, I need actually still. I can't just minimize it. There. So, 8x plus 6y, plus 6y, 6x minus 8y. Okay. So what we want is we want this to either be in the form of our q, which was this. This is the form of our q, right? Okay. Or we want it in the form of our r, this thing here, r theta. And considering we have a thing in the front, it looks similar to the q because it also has a thing in the front, right? So I'm going to take a guess and say it's that, right? And so the matrix representation of this, I could just jump right to this. It would just be negative 1 over 10. And then again, this matrix is just 8, 6, 6, negative 8. Right? Kind of actually just does it nice for you there. And we want this to be 1 over 1 plus m squared, right? 1 minus m squared, 2m, 2m, m squared minus 1. So let's just match up this and this. Alternatively, this and this, but that's the exact same thing. And solve for m. 2m equals 6, m equals 3. And let's see if that works for all of them, right? So of course it works for the two yellow ones because those are identical, right? What about this one? 1 minus m squared, does that equal 8? So 1 minus m squared equals 8. Of course, I can rearrange this solve for m. Alternatively, I can just plug in the value of m we got and see if it's true. 1 minus 3 squared equals 8. 8 equals 8. So yes, m worked for that too. Let's try this one. Maybe let's use a different color.
Wouldn't that be negative 8? Like
yeah, it's negative.
Oh, yes. I went too fast, didn't I? Okay, then let's actually solve for m here. So this would be, this would be m squared equals, oh yeah, okay, hold on.
Slope.
You have a negative outside. You don't really need. I mean, like you're getting negative 8, but you still have the negative like beside the 1 over 10.
Yeah.
So that's technically just 8.
Yeah. So I can multiply that, and then what would I get here? Then this 3 would have to be negative. Yeah. Okay. So to explain to people what's going on is that I have a problem here, right? Is that if I put in that 3, right? And I went a little too fast and I didn't notice that, right? So, sorry, 3 squared. 1 minus 9 equals 8. Negative 8 equals 8 is not true. So 3 doesn't work, right? And if I tried negative 3, it also wouldn't work just yet. So there's something wrong here. One thing, I have to start manipulating it a little bit. So let's move that multiplication in, okay? So if I move that multiplication in, that's negative 8, negative 6, positive 8, and that's a negative 6. Now let's try this yellow thing again. So it's going to be 2m equals negative 6. Right? Yeah, 2m equals negative 6. So m equals negative 3. And let's go back up to here. Let's go back up to the blue pair. And let's check if 1 minus m squared equals negative 8 is going to be the answer with this new m value. M equals negative 3. So 1 minus negative 3 squared equals negative 8. Negative 8 equals negative 8. Okay, it worked for that. Let's check now if it works for this pair. Right? So m squared minus 1 should equal 8. So negative 3 squared minus 1 should equal 8. 9 minus 1 equals 8. 8 equals 8. We're good. And finally, we just need to check if this matches up. Right? So 1 plus m squared equals 10. Right? It's 10. So 1 plus negative 3 squared equals 10. 1 plus 9 equals 10. 10 equals 10. So since m works for all these values, m equals negative 3. And so this transformation is actually q negative 3. Or is identical to q negative 3. Okay.
Do you have to put the...
Would I have to put what, sorry?
Sorry, is it just q negative 3 equal to that function, that formula?
Yeah, q negative 3 is equal to this.
For m thing.
Yeah.
Okay. Cool.
So what made you use this formula, or like the keyword that?
Well, it had a thing in the front. It had a coefficient, and so the q formula has a coefficient. The r formula doesn't have a coefficient in the front.
Okay.
So
okay.
From that, it gave me a hint that it's probably the q formula. And then yeah. Also, like the coefficients are not like things that come out of sine and cos functions. You usually don't get 8 and 6 and negative 8 out of a cos function, right? So
final answer. Sorry. Wouldn't the final answer be y is equal to negative 3x? Because you said that the qm is equal to like the reflection on the line. Y is equal to mx.
Yeah. So this is reflecting over. This is reflecting y equals negative 3x. Is that your question? Like, is that the same thing? Or?
Yep, that was it. Yeah.
Yeah.
The thing is, the question is. Oh, okay. No, the question is asking that. Never mind. The question wasn't asking for that. So yeah. So the final answer would be find the line or angle. So that is the line.
And so, do we have any formula for reflections over lines that the y-intercept is not 0?
No, we don't.
Okay. So how would we, if this was like not the line, and how do we like reverse and get the angle?
If it was the other one, so maybe let's do I think B is the angle, right? Yeah, B is the angle. So for part B of this question, because we did part D, so part B is a similar question. Txy is equal to 1 over root 2 x plus y negative x plus y. So my rule kind of breaks down. It's not really a rule, but my hint kind of breaks down here because this has a coefficient, but this I know is going to, like, I don't know yet, but I'm telling you is going to be the r theta one, right? And so the reason I would be like hinted that is the case, and the reason I even know it without looking at the answer is because 1 over root 2 is something you get from a sine function and from a cos function pretty often. And all these coefficients are just 1 or negative 1. So it looks like it's going to be the sine or cos one, right?
That makes sense.
So the matrix representation of this would be 1 over root 2 1, 1, negative 1, 1. I'll multiply that 1 over root 2, and I'll turn it into a root 2 over 2. So it's going to be root 2 over 2, root 2 over 2, negative root 2 over 2, root 2 over 2. Okay. And what I want is that since I'm guessing this is going to be a r theta one, right? R theta. The matrix representation of r theta is cos theta, sine theta, negative sine theta, cos theta, right? And so from here, I'll use this one because this is the most useful one. So I'm going to say negative sine theta equals root 2 over 2, right? And so let's just check. So sine theta equals negative root 2 over 2. Theta equals the sine inverse of negative root 2 over 2. Right, and the sine inverse of root 2 over 2 is pi over 4. And let's just check if that works for the rest of them. So cosine of pi over 4. Cosine of pi over 4 is... Oh, no, I clicked the wrong one. Cosine of pi over 4 is root 2 over 2. Sine of pi over 4 is, we know that already, but it's going to be... oh, hold on. That doesn't make sense.
Yeah, I was going to ask, isn't it like 5 pi over 4?
Yeah. So we ran into a problem because sine pi over 4 is... sine pi over 4 is positive root 2 over 2.
You could try negative.
We could try what? Sorry?
So
Negative pi over 4.
Yeah, we'll just do that.
So we'll use our cast rule. Yeah, sorry. Go ahead.
I was saying that like you can look at it. So in the thing it says square root 2 over 2, and then we know that it's a cos and then negative sign. So basically you're looking for an angle that has that makes cos positive and sine negative.
Mm-hmm.
So then that would be in the fourth quadrant.
Yep.
And so then you would have to do 360 minus 45 degrees or pi over 4, and then that's your answer.
Yep,
so that would be whatever that in radians. I don't know.
Well, that's 7 pi over 4.
Exactly. So there you go. So since we were looking here, right? Exactly what you said, right? So it's just we want cos to be positive. We want sine to be negative because remember this is just sine theta, and sine theta is negative. This is positive because there's a negative sign in the front. So we know we want to be in the third quadrant. That's where cos is positive. Everything else is negative. So to get an angle from here into the third quadrant, the same angle with the same trig. Sorry, I shouldn't say the same angle. It's not the same angle, but the same trig ratios for that angle. To get into the third quadrant, you just do 2 pi minus theta. In this case, theta was pi over 4. So 2 pi minus pi over 4 is 8 pi over 4 minus pi over 4, which is 7 pi over 4.
Yeah.
Oh, that was right. For a second, I was like, wait, I did something wrong, but no, that is.
So we were trying to find something where it's cos is positive and sine was negative, right?
That's right.
Yeah.
And so the final answer is that this is a rotation by 7 pi over 4.
Yeah.
Can we go over steps once you're finished?
Yeah, for sure. 7 pi over 4, which is identical to a negative rotation of pi over 4.
Okay.
Which I think is what the question in the textbook, like the answer in the textbook is.
Yeah. So do we just, if we were to do this on like a test, would they ask for like a positive angle, or can we just leave it in like a negative?
It's the same. I don't think they would take a mark off for it being different. It's the same number. So it's a different number, sorry, but same answer, right? Same rotation. So
yeah.
And I would always put it as a positive because I don't like it. Usually you don't do negative angles.
Yeah, true.
Right. So that's that, right? Just make this a little nicer. Yeah. Okay, so let me recap this a little bit. And this is probably going to be around about the end. I don't know if it's 9 o'clock. So I'll still do some more if someone has a suggestion for a practice problem, but I'm not going to be doing any more content today. So for this problem here, we were given this. We're trying to determine if this is some kind of reflection or some kind of rotation, right? If it's one of these two. So I have an idea that it's going to be a rotation because of this 1 over root 2, and all these are 1s. Looks pretty promising. Okay, so First I get the matrix representation of this transformation, multiply that 1 over root 2n, okay, and then I match it up with my definition of r theta, okay, and so then I start trying to figure out which ones go together. So I tried to solve for theta by matching these two. Negative sine theta equals root 2 over 2. Solving for theta, I got pi over 4. Trying that with the rest of them, I noticed that it wasn't the right sign, right? Because cos was correct, those two matched. Cos was correct, those two matched. But actually, this didn't work because it wouldn't have matched. Although I don't know how it didn't match for this if we defined theta like that. We got theta like that. But anyways, it didn't work for these two, right? Because if you look at it, we're looking for cos to be positive, right? Cos is positive, and we want sine to be negative, right? Because this is right, is negative sine. So negative, if you're doing negative sine, then and it comes out positive, then sine must have been negative, and sine's negative here. So to get the same trig ratio, but in the fourth quadrant, because that's where cos is positive and all the rest are negative, you do 2 pi minus the angle, and we got 7 pi over 4, which is the same as rotation of negative pi over 4. And that works with the rest of them.
All right, that makes more sense.
Are we going to cover eigenvalues tomorrow?
I don't know if we'll get to it, although I better move fast because we're running out of time. Let's see how many.
Hey Adam,
Hi.
I don't know if this was answered, but what if you had a reflection and a rotation? Will it matter like which operation you do first?
I'd say always act like it matters. Yes, I don't know if it actually matters. Sometimes it might not matter. Sometimes it might. If I could do an example, I don't know. I don't know if it'll matter, but I actually think that would reflection.
The question says like
does-
what has to go first.
Yeah, someone's gonna say something.
Sure. I'm not sure if it like matters reflection or rotation first. If they say something like rotate this then reflect it, that means your reflection matrix is on the right and your rotation is on the left. Like the one they say first is on the right, and the one they say after is on the left. If that makes sense.
Well, just think of it like this. Think of it like this. You're applying this transformation to the vector x. The first transformation you do is the first one they ask. So rotate. So you would do your rotate first, r theta, and then they ask you to reflect. So then you would put qm. And so that's the order you put it in. If they asked in the other order, then you would, if they said reflect and then rotate, then you'd switch the order. Right? So just think of it like applying to x first.
Yeah, that makes sense.
It does matter
Thank you.
because
Yeah, that makes sense.
when you think of it, if you have like a vector 1, 1, you rotate it 90 degrees, and then you reflect it. It's not going to be the same thing as if you reflect it and then rotate 90
Yeah.
degrees.
So try to imagine it, right? Yeah, that makes sense. It wouldn't be the same thing. It wouldn't be the same thing for sure. Yeah, would not be the same thing. So order does matter in this case.
Yo, are you gonna drop the link to this thing here?
Recording or document?
The document.
Document. Yeah, I will. I'll put it in my tutor announcements after this.
All right, cool.
Okay, guys. Well, that's everything for today. I mean, of course, keep asking questions. I'm here to answer questions, but that's all the content.
Yeah. This is going to be more like, I don't know if you'll be able to answer this one, but like, what do you think the hardest thing possible combination of like these 4 kind of sections would be? Like, could they give us a rotation reflection of a transformed matrix in R4?
Yeah, well, it wouldn't be in R4, but they could do everything else. Yeah, they could do everything else. Yeah, they could do everything else. So let's say like they would say like, I don't know. Yeah, they could stack. You could stack as many transformations as you want on top of each other, right? So if you want this to be like, here's a rotation by theta, here's just a transformation A, and here's a reflection over M, right? Well, you just do it, right? You just either multiply these two, and then multiply that with that, right? To get the matrix representation, or just multiply the vector through, right? Which is the same thing, really. And yeah.
Okay.
So yeah, they could definitely stack a couple on top of each other.
Are you doing any eigenvalues question today?
I haven't done any yet, but I will do some. I guess let's say tomorrow. Let's say I'll try to get there tomorrow. I mean, we're only on 5.5, but let's say I'll try to get to eigenvalues and do one eigenvalue example at least tomorrow.
They're probably doing study hall, by the way. So.
What'd you say? Sorry.
They might do it in the study hall tomorrow morning. So.
Okay, yeah. So
let's just like review that and not do any examples. So
wait, what time is the study hall?
10 a.m.
10 a.m.
Oh.
What do they think?
Can't wake up.
But what section is eigenvalues again?
7.1.
7.1.
Okay.
So you might just want to review the sections, not do any practice questions. Just review them.
Well, I'll probably still do some practice questions. I mean, we have the 3 hours tomorrow, right? But yeah, I don't have to do too many because there are, a lot of people are going to the study hall too.
We'll have to do
9.1 is the abstract vectors, right?
Sorry, just people asked two people at the same time. One person said isomorphism. Yes, we'll do isomorphisms tomorrow, and then another person said something else.
The 9.1, is that just the abstract vector spaces?
Yeah, that's all we're doing from chapter 9 is the first section called algebraic considerations.
Okay.
That's all we're doing from abstract vector spaces. And over the break, I will be teaching myself the rest of chapter 9. So if anyone wants to join me, just DM me, and we can do it together. But yeah.
Alright. Good night, boys.
Okay.
Wait, isn't 9.1 basically the same stuff as chapter 5?
Good night, man.
Not quite. Not quite. It's similar stuff for sure. You're like proving that. So like in 5.1, we were proving that something is a linear transformation by making it follow the rules. It's really similar to 4.11 and 4.10, where you were like proving something's a subspace. Right?
Like a section of proofs, right?
Yeah, so in 9.1, you have to prove something's a vector space. So to prove something's a vector space, well, you just have this huge list of things you have to prove are true in the vector space.
Like if it's closed under addition and scalar multiplication, right?
Well, those are just two. There's like 9 of them, I think. There's 9 things you have to prove, right?
There's 9 things. Well, 10, actually.
10? Yeah, I don't remember the number. Here, I'll put it here. Vector spaces. So but the idea is that anything at all that passes these axioms, right? The axioms of addition, there's 1, 2, 3, 4, 5, and axioms of scalar multiplication, there's 1, 2, 3, 4, 5, so 10.
Oh my god.
Right? I mean, some of them are easy to prove, like 1 times v equals v.
Not as bad
right?
as it might look.
And v plus 0 equals v.
The easy one though.
They're definitely not going to give us one whole thing like this. I mean, I shouldn't say definitely, but Horowitz said they wouldn't give us one, like, prove that this is a vector space, do all of these things. They wouldn't give us that.
Then what would they give us?
They'd probably give us like prove one of these things or prove 2 of these things or something like that, right? For this vector space. Not all 10.
So they are including 9.2.
9.1, not 9.2.
Oh.
This is 9.1.
Okay. And you said you were continuing chapter 9 over the break?
Yes, I'm doing the rest of chapter 9.
Oh, that's just for fun, though. Right?
That's just for fun.
Oh, you just want to do it?
Yeah. You just want to do it.
I'm a math guy.
So I don't understand. Like, I've never really used a textbook because it's just so.
Something to keep in mind, by the way. You're not going to need much of linear algebra unless you're going into like electrical, I think, civil.
Yeah. It's not super important for otherwise. Yeah, I'm in computer, so it's important. I also just
computer. Are you gonna use it?
All of computer is pretty similar to electrical, except you just apply it to computers. I'm pretty sure. Right. So all the math you do is identical to electrical. Right. It's because it's the same stuff. Right. It's the same. Like you're doing the same stuff. It's just one is applied to like
but all this stuff about linear transformations, I heard it's not on that. It's just like the basic stuff about determinants and like system of linear equations, right?
I don't know. Yeah, I don't know.
We'll cross that bridge when we get there, boys.
Definitely. If anyone's in computer science, they're gonna use like computer science uses all this stuff, right? So maybe I'll use it in computer. I don't know. Any kind of 3D modeling or rendering uses all of this.
Yeah, because also if you do environment, you're also gonna do My senior is a fourth year. He says like you're still using linear algebra. There's no escape.
Yeah.
If you're in computer, right?
He said biomed, I think. This guy said biomed just now.
Oh.
Yeah. Yeah.
Use it in every discipline, I think.
I don't know. Well, you use some of it. I mean, it's all useful math, right? Not all, sorry. Some of it is useful math for everything, right? But not all. Sorry, just at all. But it's I don't know. Depends on your discipline, I guess, right? So.
I'll take calculus more oriented to all disciplines instead of linear algebra. That's why I kind of know how.
Yeah, calc obviously.
Yeah.
Calculus
But
is.
It's up to you guys what you want to do over the break. Good luck if you do it.
I have some plans over the break.
Yeah.
They have this like a winter thing. It's like a mini course thing.